Hello, everyone. Thank you for joining us in this third day of our conference in ICMAM 2024. Welcome again. We hope you enjoyed this morning and all this day of conference. For today, for our field store, for me it's a huge honor to introduce to Professor Efim Selmanov. Professor Selmanov was awarded in 1994, as a field medalist. So for us, it's a huge honor to have Professor Selmanov in our conference. I would like to do a brief remark before to start. Professor Selmanov cannot be online in our conference. However, he record his talk in advance, so we will see his talk in video. But I would like also to say that we don't have a space for question or comments. So we hope enjoying the conference, and please, Brian, go ahead with the video by Professor Selman.
Just give me a second, please. I'm trying to share my screen now. Can you see the screen?
Yes. We cannot hear Brian.
Now, can you hear?
No.
Let me see.
Maybe you can stop the sharing screen and try again, Brian.
Opportunity to speak at this wonderful conference. I will talk about.
Now?
It's perfect.
Okay. Okay, right. Let's go ahead.
Opportunity to speak at this wonderful conference. I will talk about growth and complexity functions. Growth of what? Of all infinite objects that can grow. First of all, growth of groups, algebras, even formal languages. Let us start with groups. This is the most classical part. Suppose we have a group G, which is finitely generated. Well, it is generated by elements x1, x2, and so on up to xm. It means that an arbitrary element of the group can be represented as a product of generators and their inverses. Now let us consider the finite subset that consists of products of bounded lengths. if we think of a Kelly graph of this group, then clearly this is a ball of radius n with the center at the identity element. These balls grow, and their union is the whole group. Now, since all these balls are finite subsets, we can discuss the number of elements in these balls. Sometimes it is referred to as volume. Unfortunately, and this is a growth function, g of n, but I write here x because this function depends on the choice of a generating system. If you choose another generating system, you get a different function. Therefore, we need to introduce some equivalence. Let n, capital N, be the set of all positive integers. Given two functions on positive integers with value, well, in this semi-infinite segment, so suppose that we have two increasing functions. We say that f is asymptotically less or equal than g if there exists an integer constant c such that this inequality holds for any n. If f is asymptotically less or equal than g, and g is asymptotically less or equal to f, then f and g are equivalent, asymptotically equivalent. This is a very rough equivalence. For example, two polynomials are asymptotically equivalent if and only if they have the same degrees. And if you choose two generating systems in a group and both systems are finite, then the growth functions defined by these systems are asymptotically equivalent. Therefore, the growth of a group is not a function. It is a class of equivalence, of class of asymptotic equivalence. Motivation. Originally, motivation comes from geometry. Schwarz, Yefremovich, Milner proved that if you have a Riemannian manifold and fix a point, then the growth of volumes of balls centered at this point is asymptotically equivalent to the growth in the fundamental group of this manifold. Another reason was just comparison of infinite groups. If you have two finite groups, you can say that one of them, say, contains more elements than the other one. But if you have two finitely generated countable groups, how can you compare them? You can discuss which one grows faster. It's an invariant. And the same concept can be defined for monoids. Monoids is the same as groups, but there is no inversion. It can be defined, let us define it for hereditary languages. What is a hereditary language? Suppose that we have a finite alphabet, which consists of letters A1, A2, up to AM. A word is a finite sequence of letters, including the empty word. And we select a set of words that we call bad words. They are prohibited. So the language consists of all words that do not contain bad words as subwords. It is called formal language. Words can be multiplied, and if you add 0, then it is the same as monoid defined by generators and relations, where all relations look like this. W sub I are bad words. Stepin and Grigorchuk found some explicit formulas for the growth of these languages. growth of a language, the function of growth, is the number of words of length n. Now let us talk about algebras. Suppose F is a field, and we consider an algebra generated by a finite dimensional subspace V. So it's a finitely generated algebra. But generally speaking, I never said that the algebra A has to be associative. Such concepts are considered also for Lie algebras and for other non-associative algebras, but today we consider it for associative algebras. So let V to the power n be the span of all products, well, k, where k is less or equal than n. So all products of lengths up to n of elements from V. Of course, this product is not a subspace, but you consider the span. And these subspaces are finite dimensional. They are embedded into each other, and their union is the whole algebra. So we can define the growth function as the dimension of V to the power n. Again, it depends on the choice of the generating system V. You choose another system, you get another function. But if you choose two finite dimensional generating subspaces, then their growth functions are asymptotically equivalent. This concept, well, it was first considered by Gelfand and Kirillov. They defined Gelfand-Kirillov dimension if this function is bounded by a polynomial. And this is the property that does not depend on asymptotic equivalence. If a function is bounded by a polynomial of degree n, then any asymptotically equivalent function is also bounded by a polynomial of the same degree. So the minimal alpha such that n to the power alpha, not minimal, infimum of the set of all alphas with this property is called Gelfand-Kirillov dimension of the algebra A, some invariant. Gelfand and Kirillov needed to show that two infinite dimensional finitely generated algebras were not isomorphic. So they introduced this invariant. In 1968, John Milner published a very influential survey in Mathematics Monthly. As you know, Mathematics Monthly is a journal for students. In that survey, he formulated two problems on growth. The first problem, is it true that a group has polynomially bounded growth if and only if it has a nilpotent subgroup of finite index? At that time, it was known that a finitely generated nilpotent group has polynomially bounded index. There were formulas to find this index. What am I saying? It was known that finitely generated nilpotent groups have polynomially bounded growth functions. And the degree of this polynomial was known. And it's also more or less obvious that the growth of a group and subgroup of finite index are asymptotically equivalent. So the question, so these groups have polynomially bounded growth. The question was if they are the only groups that have polynomially bounded growth. And another question, do there exist groups of intermediate growth? Intermediate means that the growth function grows faster than any polynomial and slower than any exponential. So it lies in between. Both problems were solved within 3 years. in 1980, Gromov proved that indeed a group has polynomially bounded growth if and only if it is virtually nilpotent. So it has a nilpotent subgroup of finite index. And I should say that his proof was at least no less interesting than the result. It was the beginning of geometric group theory as we know it now. And the second, well, so this is still, okay, let us talk a little bit more about Gromov's proof. In 1972, Jacques Tits proved his famous Tits alternative. Every finitely generated nilpotent group is either virtually solvable or contains free subgroup. For solvable groups, the positive answer to Gromov's question was known. It is Joe-Wolf. And if it contains a free subgroup, then the growth is exponential. So for linear groups, the answer was no. Now, Gromov's idea. This is a group G. These are elements of the group G, and we consider the Kelly graph. And every connected graph can be viewed as a metric space. We just say that the length of every edge is equal to 1. So this is a metric space, but this is a discrete metric space. And this, well, I tried to draw a helicopter. This is a helicopter. It goes up. We sit in this helicopter, and this group G becomes more and more distant, and the distance between points becomes smaller and smaller. It's some limit process. And the limit is a manifold. And the group acts on this manifold. And then Gromov proved using Hilbert's fifth problem that it is linear. If it is linear, then he could use Tits's result. Well, later, the proof of Hilbert's fifth problem is already a considerable proof. Later, Bruce Kleiner invented a proof which did not rely on the positive solution of Hilbert's fifth problem, but it also uses the same geometric ideas. And the second question of Milner was answered in 1983 by Rostislav Grigorchuk. He constructed a group of intermediate growth. If you consider a rooted tree, this was a group of automorphisms of this tree. And the growth was faster than any polynomial and slower than any exponential. Now we could ask, what is the growth of the Grigorchuk group? It's an interesting story. Consider this cubic equation. It has a root which is approximately equal to this. And we take the logarithm of 2 with the basis of this root. It is approximately equal to this. Now, Laurent Bartholdi, Anna Erschler, and Tianyi Zheng showed that the growth of the Grigorchuk group is asymptotically equivalent to this. Bartholdi showed that this is the upper bound, and more recently, Erschler and Zheng showed that this is also the lower bound. The paper, if you look at the paper, you won't understand that this is a paper in group theory. It's rather random walks, a paper in probability theory. Now, the basic question for groups, algebras, monoids, and any other structure is which functions appear as growth functions up to asymptotic equivalence. If So it's obvious that not all functions. If g of n is a growth function, then it is an increasing function, of course, and it is submultiplicative. Why? If you consider a rod of length m plus n, it is a product of a rod of length m by a rod of length n, and this immediately implies this inequality. Now, the question was, is it true? And still is, by the way. It's not known. Is any increasing function which is submultiplicative asymptotically equivalent to a growth function of a group? Bartoldi and Escher showed that if the function lies, if a function lies between the growth of the Grigorchuk group and exponential, plus it is sufficiently regular, and sufficiently regular here means that I don't want to list all the conditions, then yes, it is asymptotically equivalent to the growth of a group. There is a conjecture due to Grigorchuk that there are no growth functions in this gap. There is nothing between polynomial and e to the power square root of n. And Grigorchuk proved it for residually p groups, that is, groups that are subdirect products of finite p groups. Let's talk about algebras. And first of all, about Gelfand-Kirillov dimension. Well, it is easy to see that the algebra has zero Gelfand-Kirillov dimension if and only if it is finite dimensional. Now, the polynomial algebra has Gelfand-Kirillov dimension 1. There is nothing between 0 and 1, because you remember this generating subspace V. It lies in V2, lies in V3, and so on. If, at least at one step, we have stabilization, then that's it. It doesn't, then you achieved full stabilization. So the algebra is finite dimensional. If at each step the dimension grows at least by 1, then you already have a linear function. So Gelfand-Kirillov dimension is at least 1. So there is nothing between 0 and 1. Hedlund and Morse in 1938, and then George Bergman in 1970, proved that there is also nothing between 1 and 2. It's less trivial. And starting with 2, Bohr and Kraft constructed algebras of an arbitrary Gelfand-Kirillov dimension. Now, what about the problems that I already formulated? Which functions appear as growth functions? Of course, they are increasing, they are submultiplicative, doesn't guarantee that they appear. Laurent Bartoldi and Agathos Maktonovich showed that if the function is increasing and submultiplicative, then there is a growth function which is close to it. So lies in this, well, in this segment. And here I also want to say that there are more algebras of intermediate growths than groups. So Grigorchuk's groups act on a tree. Later, many other examples of groups of intermediate growth were constructed, but depending on the distance from which you look at these groups, they are all close to Grigorchuk groups, in some sense. It would be interesting to find completely new examples. Martha Smith proved in 1976 that if L is a Lie algebra of sub-exponential growth, then the universal enveloping algebra also has sub-exponential growth. now let us consider, let G be a finite dimensional Lie algebra, and we consider polynomials in one variable with coefficients from G. Then the growth of this infinite dimensional algebra is linear. So it's sub-exponential. It means that the universal enveloping algebra also has sub-exponential growth. And it is not polynomial, because from Poincaré-Birger-Witt theorem, it follows that the universal enveloping algebra has polynomial growth of finite Gelfand-Kirillov dimension if and only if the Lie algebra is finite dimension. Now, the description of growth functions of algebras, monoids, and hereditary languages. You see, groups are not mentioned. I will talk about our joint work with Jason Bell, which gives description of growth functions of all these classes, not including groups. Let capital F of n be an increasing function, and small f of n be its discrete derivative. This is the joint theorem with Jason Bell. Suppose that the derivative is greater or equal than n plus 1. The derivative is submultiplicative, and we also have this inequality. You may ask why this inequality does not follow from submultiplicativity. It's because I never said that this derivative is an increasing function. That would mean that the second derivative of f is positive, but we don't assume it. So if you have a growth function, then these conditions hold. And we proved that if these conditions hold, then f, capital F, is asymptotically equivalent to a growth function of a hereditary language. We constructed this language. If hereditary language can be viewed as a monoid with zero, as I explained before. And the growth of every monoid is equal to the growth of its semigroup algebra. So it is a growth function of a hereditary language, or monoid, or an algebra. Now, since all the conditions are imposed on the derivative, and on the derivative, submultiplicativity for the derivative is stronger than submultiplicativity for the function, because inequality can be integrated, but inequality cannot be, it does not extend to derivatives. It cannot be differentiated. So after this theorem appears, Beery-Greenfield immediately constructed an increasing submultiplicative function such that the function is submultiplicative, but the derivative is not. So it is an increasing submultiplicative function, which is not asymptotically equivalent to a growth function. Now I'm going to talk about another problem which existed for some time in symbolic dynamics. Let's talk about complexity functions. Let x be again the alphabet, finite alphabet. X to the power n is the set of infinite words. The complexity function is p of n, is the number of subwords of length n. The smallest complexity, again, Hedlund and Morse, did the same result as the one that I quoted before. They showed that the smallest complexity function of a non-periodic sequence is n+1. And such sequences are called Sturmian sequences. It corresponds to Gelfand-Kirillov dimension 2, especially interesting case. I said before that there is a gap between 1 and 2, and starting with 2, every number is Gelfand-Kirillov dimension. So 2 is the borderline case. It corresponds to Sturmian sequences. You know, if you have a Sturmian sequence, any infinite sequence, you can view it as a number in Q-adic expansion. You know, Q is, we have Q letters. This is a number in Q-adic system. And Ferenczi, Modit, Adamczewski, well, many authors proved, there were a sequence of papers, that if the sequence is Sturmian, then this number is transcendental. There is a lot of similarities between growth of algebras groups and complexity function. More generally, we can talk about complexity functions of a hereditary language with a number of words of length n. It is an increasing function. It is again submultiplicative. A word of length n plus m is a subword of length n, and then you write the subword of length m. Well, and if it is not linear, then it is, well, if it is not periodic, then you have at least this. In our joint recent paper, you know, there was a problem of classification, description of all complexity functions, but it was not clear how even to approach it. Description in which terms? After our theorem on growth functions, it became clear that at least one has to try to classify complexity functions up to asymptotic equivalence. And we did it jointly with Biri Greenfeld and Carlos Gustavo Moreira. Let f be a non-decreasing function satisfying this condition and this condition for every n. Then there exists an infinite word such that f is asymptotically equivalent to the complexity function. So these are conditions. You know, complexity, if you compare complexity functions with growth functions, then complexity function is the analog of a derivative of growth function. So the conditions are very close. And in our paper with Jason Bell, we constructed that language, but there were words that are not extendable to an infinite word. Extendable words are of particular interest. Therefore, that theorem did not cover the case of complexity functions of infinite words. And this proof, I would say, is more complicated. Well, and corollary, if you have a non-decreasing submultiplicative function, there exists a finitely generated simple algebra of an arbitrary field whose growth function is close to it. So it's even growth of simple algebra, finitely generated simple algebras. It follows from the result on complexity functions. Now, of all algebras, nil algebras are the special class. An associative algebra is called nil if an arbitrary element is nilpotent. For many years, the main problem in ring theory was Courage problem. If there exists an infinite dimensional, finitely generated associative algebra that is nil, that is the analog of the Burnside problem for groups. In 64, Golod and Shafarevich constructed counterexamples. Well, strictly speaking, Golod constructed these counterexamples, but it was proved, it was based on Golod-Shafarevich inequalities. Then Latyshev and Small independently formulated the question, okay, there exist finitely generated infinite dimensional nil algebras, fine. What if they have finite Gelfand-Kirillov dimension, so polynomially bounded growth? Do they still exist? If we talk about the Burnside problem and groups of polynomially bounded growth, then no. Because by Gromov theorem, every group of polynomially bounded growth is virtually nilpotent. For virtually nilpotent groups, the Burnside problem has positive solution. What about algebras? For algebras, surprisingly, the answer is that they do exist. Tom Lenagan and Agatas Maktunovich constructed such examples, but only over countable fields. For uncountable fields, the question is still open. Then Tom Lenagan, Agatas Maktunovich, and my student Alex Young constructed a better example whose Gelfand-Kirillov dimension was between 2 and 3, but it is not known explicitly. Now, what can we say about growth functions of nil algebras? My conjecture is that if for any function that satisfies the conditions of our theorem with Jason Bell, so which is asymptotically equivalent to the growth function of any algebra, and it is greater or equal than n squared, we don't consider trivial cases, then this function is also asymptotically equivalent to growth function of a nil algebra. The meaning of this conjecture is that there are many nil algebras. So all growth functions appear already there. Now I will formulate some theorems, and they are all joined with Beery-Greenfield, and they all appeared already in advances in mathematics. And we assume, well, we formulated theorems for algebras over countable fields and algebras over arbitrary fields. Over countable fields, you can say more. So just for the sake of simplicity, let us assume that our field is countable. But I'm saying that these results can be extended. Let P of n be the growth function of the Lenagan-Maktunovich-Young algebra. So this function lies here, but it is not known explicitly. Let f of n be an arbitrary increasing submultiplicative function. Then this function is asymptotically equivalent to growth of a finitely generated nil algebra. You know, if the function f of n is superpolynomial, then multiplying it by a polynomial doesn't change much. Now, oscillating growth. In 2013, Martin Kasabov and Igor Pak constructed groups with oscillating growth functions. and they were oscillating between a given intermediate function, something like that, and an arbitrary rapid exponential functions. So infinitely many times it was smaller than this, and infinitely many times choose any function that grows faster than this one. The example was also, I would call it Grigorchuk type group. Then Viktor Petrogradsky constructed analogs for nil restricted Lie algebras of positive characteristics. Well, he constructed also, there was our paper with Ivan Shostakov, restricted Lie algebras that behaved like Grigorchuk groups. And so he also constructed oscillating growth functions, but only over fields of positive characteristic. In our paper with Beery, we constructed associative nil algebras of arbitrary characteristic with oscillating growth function. And from an associative nil algebra, you can easily construct Lie nil algebra. So we can do it on over arbitrary characteristic. More precisely, this is the theorem. Let F be a countable field. Let f of n be a sub-exponential function. Then there exists a finitely generated nil F algebra such that the growth function satisfies this inequality infinitely many times, and this inequality infinitely many times. One could ask here further questions. So both sets are infinite. One could ask, can we make it that both sets have positive measure? You know, there are various ways to define measure on sets of positive integers. And even there exist domains with oscillating growth functions. So there exists a finitely generated domain. Domain means that no zero divisors. A product of any two non-zero elements is not equal to zero. So infinitely often the growth function satisfies this inequality, and infinitely often this inequality. You may choose your function f being essentially bigger than this function. Well, so basically I said everything that I wanted to say. There are many open questions that still remain. Of course, the number one, what are growth functions for groups? Our method did not cover groups. Grigorchuk's conjecture on the gap between polynomials and e to the power square root of n. For algebras, there are many questions about algebras of Gelfand-Kirillov dimension 2, this borderline case, which is close to Sturmian sequences. Still, well, and there are still open questions about complexity functions, which I probably won't formulate. Thank you.
Thank you, Professor. Maybe I have a question.
Good.
You say that, for example, you can relate growth functions with the fundamental group of a manifold. I want to know if there is something related, for example, with curvature or something for the case of Riemannian manifold. I mean, if you
No, I'm afraid I don't. I cannot hear you well. Can you make it louder?
Okay, yeah. Are you listening to me now?
Oh, now it's better.
Okay. Now my question is that at the starting you said that you can relate the growth functions with the
Well, not me, it
fundamental.
was Schwarz, Yefremovich, Milner.
Okay, yeah, yes. So I want to know if there is something that relates, for example, curvature of Riemannian manifolds with growth functions, because the fundamental group you only have the topology, right? But concerning the Riemannian structure, you can relate that in some way with growth functions. That's my question.
Good question. Now I cannot say anything, but good question.
Okay, Professor. So that's it. Thank you for being here. Thank you for your nice talk, and thank you for
Thank you.
supporting our event. Good night and good trip in China.
Thank you. Thank you very much.
Bye.
Bye.
Bye-bye.
Okay, to end this video talk by Professor Selmanov, we would like to express our gratitude to Professor Selmanov for accept our invitation to this meeting, and also for take the time to record the talk in advance before his trip. So we are very grateful with him. I think we can start in maybe 7 minutes with the next talk by Professor Analisa Bufa. So see you in 6 or 7 minutes.
Professor Buffalo, can you mute yourself, please? I already,
I am muted. I was muted.
yeah, you are muted now. Welcome, Professor Buffalo. Maybe we're starting in about 7 minutes, but maybe if you can try to share your screen to check that everything is working, it would be okay. You are muted, Professor.
Okay, can you see my screen?
Yes,
Okay, wait, can I move it?
perfect.
Okay,
Hmm?
yeah. Okay, perfect. Then I can stop sharing. And you hear my voice clearly, right? Do I need to wear a headset?
Yes, it's clear. And we're hearing you well.
Okay, perfect. So see you in 5 minutes or so. I will
Okay.
be here.
Mhm.
Okay.
Okay, I think we can start now. Please share your screen again, Professor Buffa. Is it Buffa or Buffa?
Buffa is
Buffa?
fine.
Buffa. Okay. You're seeing your screen now. Okay, it is my pleasure to introduce Professor Annalisa Buffa, a distinguished Italian mathematician specializing in numerical analysis and partial differential equations. Currently, she's a professor at the École Polytechnique Fédérale de Lausanne, where she holds the chair of numerical modeling and simulation. Professor Buffa has made significant contributions to the field of mathematical modeling, and today she will speak about geometric simplification in design and simulation. Thank you, Professor Buffa, for accepting our invitation, and I want to thank to the participants also for joining us today.
Thank you. Thank you very much. Can you confirm how long can I speak? Sorry.
It's a 45 to 50 minutes.
Okay.
And the rest is for questions, maybe.
Yes. Okay. Thank you very much. Thanks. So thanks a lot for the invitation. I'm very happy to have the opportunity to present my recent result. And today I want to speak about geometric simplification in design and simulation. This is a joint work with some of my collaborators, and yeah, you see the names there. So the main so the framework where we move is what is called the design through analysis, which is actually an everyday reality in, say, engineering, in computational engineering, in manufacturing, in more in general. In fact, if we have imagine that we have an object and we want to know his the behavior of the object. Imagine that is just a piece of a car, and we want to know the resistance. We want to know the behavior in the real world, the behavior of the object in the real world. Then we take the design of the object, and in fact, from the design, we need to construct a computational mesh. A computational mesh is a partition of the domain into simple pieces that can be tetrahedra or cubes or deformations of tetrahedra and cube. In order to do this process, I mean, to represent the geometry this way, we basically need to remove a certain number of details. As you see here, in order to construct, I mean, I've constructed the mesh, what I call the mesh, that is the splitting into tetrahedra, say, not of the real design, but of a simplification of the design, and and I simplify, so this design is simplified and then it is meshed. Sometimes the mesh, I mean, the meshing process is complex, sometimes also need repairing, so I construct a mesh that is not good enough and I need to manually modify it. And once I have this representation of the geometry, then I can run my numerical simulation, so I can have a physical model, run the physical model on the object itself. So what you see here are examples of simplification. So this is a complex domain, and this is the simplified object that is meshed, and then on which then the physical model are simulated. This is another example of simplification where you see that the original engine was very complex, and then in order to run a simulation, the CAD system, so the computer-aided design system, performs a simplification of the geometry in order to be able to run the simulation of the physical behavior. Okay, now I do like this. So I will be using the word geometric simplification and the word the featuring in say a bit in an interchangeable way. It is actually the same concept. So let's talk a little bit about the meshing and the reason why we need to simplify the geometry. If we have a complex geometry, like, I mean, this is a mock example that I will carry along my talk just to give, say, to follow the ideas. But if I have a complex geometry like this one with holes and printed letters and so on, those small details are called features. And then there are many ways to deal with features and meshing. So I can decide to remove the features and then to reintroduce the features via what is called the trimming or immersed technique, which means that I have a valid mesh of the simplified geometry, and then the features are just put inside by cutting the mesh. So I do not have a valid mesh of the complex geometry. I have a valid mesh of the simplified one, but I carve the features inside. What happens if then I try to run my numerical simulation? Well, one of the milestones of a numerical simulation is the definition of quadrature formula. So I need to be able to integrate functions over my mesh. And of course, if features are carved inside, the integration is cumbersome. And also the stability and the accuracy of the physical model, of the simulation of the physical model, are difficult to control and to check. This is a simplified example, so you have to imagine that the underlying mesh is the one made in quartz, and then I carve my object inside the mesh. Then I could do that, but I encounter a number of problems when I do that. The other possibility is to introduce the features by meshing. So you see here, this is a mesh of the entire object that has been meshed together with the features. This generates severely fine meshes that sometimes are very complex to handle. And not only that, the meshing problem may just, I mean, the meshing problem is not always well posed and may simply fail. Moreover, the fact of meshing all the details means that, as it's written, the mesh can be severely fine. For example, just my simple object here requires 75,000 tetrahedra to be meshed if I keep all the details, and only 15,000 if I don't keep the details. Of course, I mean, these are just a mesh of comparable precision, and you see that being at comparable precision, but if I have all the details inside my geometry, the meshing process may fail, and moreover, the mesh can be extremely fine. If you think, for example, that you are solving a forward, that you're solving so with an explicit, you are advancing in time. For example, you are solving wave equation and you advance in time with an explicit scheme, then a fine mesh may be a complete killer of your simulation. So the presence of the features sometimes is really a bottleneck. So that's why features are removed. Okay. These are examples of geometric simplifications are basically in two main big categories. The first one is the one I'm interested in this talk, that is when the equations stays the same, but just the domain changes. So the geometry is simplified by just say simplification. The other one is when also the other one is the one that I represent here on the right, and there are many examples, but here I just take one. Imagine that you have a structure like this that is made of several thin layers. Then, for the sake of the numerical simulation, one can think of reduced dimensionality. So instead of having thin layers are replaced by just plates or shells. So in this way, the geometry is reduced from 3D to a collection of 2D pieces. And in this case, also the equation changes. And there is a large literature that explain how far is the solution, say how complex, how the error that I commit when I simplify and I reduce the dimensionality of my geometry. But in this case, the problem is a bit more is not completely solved, and in fact it's what I'm interested in. And the state of the art today is basically that the simplification at this level is based on purely geometric considerations. So I remove details just because they are small enough according to a certain metric that is defined by the CAD software, or say by the CAD department, and it has nothing to do with the physical problem that I want to solve on my geometry. So it's handled in the CAD system. There are buttons, you push simplify, and you get a simplified geometry. And this is regardless of the physical problem that you want to simulate on the geometry. So the question that I try to answer in this talk is, okay, but once I do that, how do I measure the error that I'm doing on the underlying PDE, so on the physical model that I want to simulate on the structure? This is exactly the question that we want to answer in the most possible general way, and in order to. So, and then this is the outline of my talk, and I will take you across several steps to try to answer to this question. So the first line is I explain what is geometric simplification or defeaturing, which I already did, and I will define a concept of analysis-aware geometric simplification, where here I really mean I want the simplification to be. I want to know the impact of the simplification on the simulation of the physical models. And then, so basically, I want to know what are the features that matters and the ones that do not matter. And I want the physical model to tell me if there are important features that should be kept, or if or others that can be neglected. And I will approach the problem via a posteriori error indicators, and I will provide a few examples, which I hope will be illuminating. And through the examples will be both, say, purely academic validation. So we will validate the efficiency of our indicators, and we will also look at a slightly more complex problem and to see the theory that we develop at play on slightly more complex problems. And sorry, my thing goes up and down. And at the end, I will also discuss the interplay between the geometric simplification and the discretization error. Because in fact, in order to optimize our effort, we would like to keep all the errors and all the error that we do under control, and possibly to be balanced in order not to use our energy to get a super nice solution on the wrong geometry, which still will provide the wrong solution at the end. Okay. Let me, okay, sorry, I am in trouble moving my slides. Okay, so I go on a very simple problem, and I try to formulate my problem now in mathematical terms. So this one is my new complex geometry, where you see that I have blue details and red details. The red details are called positive because they are yes, because they are called positive, and the blue one are called negative. And this on the right, omega 0, is my simplified geometry. On these two, and I want to solve the easiest possible PDE for the moment. And so the PDE that I'm gonna look at is the Laplace problem on the. So U is the solution of the complex is the solution of the Laplace problem on the complex geometry, where I have set a Dirichlet boundary condition somewhere on the pink region, and I have a Neumann boundary condition on all the details, positive or negative. This is very important because all what I will be saying works for a Neumann boundary condition, and it will be extended to to say more general boundary conditions, but only in a little bit. So my simplified problem is much easier because I have again the Dirichlet boundary condition, then I have the Neumann all around, and the question that I want to ask to myself is the following: Can I construct an estimator based only on the solution of U0 and not of U, because I have to imagine, I mean, I want to play the game that of course is not true in my simplified problem, but say the statement that I want to make is without being able to compute U, because imagine that I cannot construct a mesh for the domain omega. So without knowing U, I would like to know what is the difference between U and U0. So can I have something that I can compute so that I can bound the error between the solution on the complex problem and the solution on the simplified problem? Because this is the everyday reality. Solutions are not computed on complex domains, but they are computed on simplified domains. And I would like to be able to measure the distance, and possibly, as I said in the outline, as a second step, in fact, what I compute on a simplified geometry is not the exact solution, but it is a computed solution. And then I will be wanting to know the distance between U and the approximation of U0, but this is a second step. Yeah, this is what I want to compute. Just a detail, of course, because the error are computed on omega. When I have positive features, I will need to extend the solution U0 on the positive feature, and I think I will have a slide, a quick slide about that, but this is just a detail and you should not focus on this point. Yeah, so that's this is the slide. So if I have a positive feature, it is green now, I apologize for the mismatch of the colors, then basically what we do is that you have to imagine that I construct a box that is called in the CAD say terminology is called a bounding box of the feature that I called F tilde, and then I extend my solution U0 on the bounding box. You have to think the bounding box is something convex, easy, so I can mesh the bounding box and I can extend my solution outside in order to have something something that I can compare with U. Okay, as I said, this is just I mean it's an extra computation that I need to do in order to have in order to be able to construct to have something to compare with, but in some sense this is a minor point. What is important is what are the ground rules that I allow myself on the designing of my estimator epsilon U0, that is the object that I hope it will estimate the error. So this guy needs to be cheap to compute. I don't want to run very tough computation to compute the estimator, otherwise nobody will be interested in computing the estimator. And it should not require any global reparameterization. This is very important because, as I said, my assumption is that I cannot mesh the complex domain, and I can only compute integrals and fluxes of U0, or possible the extension of U0s on the features boundary. This is, say, it's a constraint that mostly come from the way CAD systems represent geometries. So the features are represented through the boundary, through what is called their boundary representation. So their boundary is represented, and this is the only information that I have on the features. So I must be able to construct my estimator based only on the CAD geometry that I have, without any need of say heavy process the complex geometry. Okay. So all the analysis that we developed is based on actually an error representation. This is the error representation. I just draw a very simplified geometry here. You can think is the L-shaped domain of before, or even more complex, but just for the sake of representing something easy here, imagine that I have one feature that is this one. Okay, so the domain omega is the square minus the feature, and the domain omega 0 is just the square. the analysis that I present works in a very general context, but let's fix the ideas in this situation. Then the distance between u and u0, so the integral of the h1 semi-norm is actually equal to this guy. So this is an exact error representation, and now I can start trying to estimate what is on the right with the constants that are as explicit as possible with respect to the feature f. So we can design an estimator that is what you see here, where d gamma is just this guy. So if we look at this guy, we can ask ourselves, what is this? So G is the Neumann boundary condition for u on the boundary gamma. And the du0 dn is the Neumann data for u0. So this guy is just the mismatch in the Neumann boundary, in the Neumann data on the boundary gamma, the green boundary gamma that you see here. So I just I go with Sobolev estimates, and basically I find an estimator like the one that you see here, where I have a suitable, say, scaling with respect to the length of gamma. So this is the length of gamma, and this is d gamma, so this guy minus the average, plus a certain constant that is depends on the length of gamma in a weak way, time the average. The average. Now, if you look at what the average is, so the average of the gamma is this guy, yeah? This is the average of my Neumann data. So I can process this and I get this quantity. So this quantity is basically the Neumann compatibility around the feature. So this is a capital F, I'm sorry. So this is the Neumann compatibility around the feature. So either it is 0 or it is not 0. If it is not 0, then this quantity pops up. It is in the estimate. And basically the kind of theorem that we have is that with this estimator, where you see that the dependence on the length of gamma is made explicit, then with this estimator, we have that the error of u minus u0 is estimated from above and from below by this specific estimator when I have only one feature that I have called f. That's why it's called epsilon f, and the constants are independent of the size of the feature at this point, because the size is kept into account by the fact that I have tracked the behavior of the constant with respect to the length of gamma. Now, if I imagine that I have more than one feature, as it was before in my L-shaped domain, the estimator is just, so I would obtain a similar estimate, but where the estimator now is the sum of the estimator for each feature. Okay, so I can continue. And so what happens in the case of the positive feature? It's again I have an error. I have an error representation that works like this. So the error between u and the extension of u0 is equal to 2 Neumann data. Is actually I need to take into account 2 Neumann, say, mismatch. So the first one is on gamma 0. Gamma 0 is this line, and yes, so I have G tilde, that is the extension of the Neumann data in here, minus the Neumann data of my simplified solution on gamma 0, and then I have another, again, the same Neumann error, but this time on this curve, because I extend my solution u0 on the bounding box that you see there, f tilde, and then I have a u0 and I can compute this guy on this boundary now. And okay, there is a minus sign just because the normal flips, but don't worry about it. These are just the Neumann mismatch between the solution, the simplified solution, and the real solution that I don't have, that is U. Okay, U carries a boundary, carries Neumann data, and then I have these mismatches. Then again, I can perform, basically it is a true Sobolev estimate. I can compute an indicator that is made of two pieces, and each of these two pieces has exactly the same shape as before. So you see there, and so I need to track the behavior of the constants with respect to the length of gamma, and then I can provide the same estimate as before. And the picture that you see here on the right is just to say that in fact positive features and negative features can be put together also in what we call complex features. So in fact, the theory that we do works for very general features. Even, you know, this is just one example where you have a positive part, a negative part, and exactly the same estimate can be extended to treat this case. Okay, now I want to give you an idea of the. So I want to test, basically. If we go back, we have this estimate here at the bottom, and we want to test if this is true. And also we want to know, I mean, these symbols denote constants. And as you have seen, I have neglected this part. And I just, for people who are very familiar with adaptive methods, it is natural to have oscillation terms on the one side of the estimate. Those terms are high order terms that are usually neglected. If you are not, so I will just neglect them all along. And if you are not, say, familiar with adaptive techniques, just believe me that those here inside, I have high order terms that I will not see in my numerical results. Okay, so I want to test this. I want to validate this. And how do I do? Well, I just that is what I do. So let's first at the domains here. So I have 4 tests that I showed to you, and these are directly in 3D because all what I'm doing, I mean, the small n was the dimension of the space. So all what I'm doing is works in any dimension. So I take a cube and I take a feature that is here in the middle, or I can take a feature that is on a corner of the cube. Those are negative features, or I can take positive features. It could be in the middle of the face. Here we take in the middle of an edge, basically, and the positive feature can be close to a corner of the cube. And then I basically construct an overkilled mesh. So I just, of course, I do numerical simulations because U0 is known because it's the solution of the Laplace problem on the cube, but U is not known because U would be the solution of the complex geometry, where you see that I do this sign, meaning that the geometry is not so complex, but still it is the cube minus the small cube or plus the small cube. So I do not have an analytic representation, but I can compute a very accurate solution U, and I can compute the errors. So the errors that you see here, I mean, all the orange line represent the error and the behavior of the error with respect to the size of the feature. So I can put I can put a very small feature, or still, you see, so this is the size of the feature is basically the diameter of this cube that you have on the x-axis, and on the y-axis you have the error. So you you have the error and the estimator. So the orange lines are the errors and the blue lines are the estimator. So for example, if we focus on the domain omega 2, the orange line is the error that you see there. So it's really U minus U0 in the energy norm, and the estimator, so my epsilon that I have computed with the formula that I gave to you, is the blue line. So the dashed blue line. So you see that in fact the estimator is a very good estimate of the error, and everything scales well with the size of the feature. This is very important because I want to be able to run estimators that, they need to scale well with the size of the feature or they will never be good enough. So this is the behavior for omega-1, for example. So again, the blue line is the estimator, the orange line is the error, and on the right you see the positive features. Again, you see that our estimator are extremely good approximation of the error itself. So I can trust that instead of computing the error, I compute the estimator in some sense. And the important thing to remember is that the estimator can be computed without computing the solution on the complex domain, just computing the solution on the simplified domain plus integrals of the solution on the feature boundary. Okay. So now I want to show another example. Imagine that I'm solving again the Laplace problem on this domain with a lot of holes now, and in fact the solution that I compute one specific solution, and the solution is the one, it is the one in the color code that you see below here. Okay, then I start numbering my features 1, 2, 3, 4, 5, etc. until 25, and I have chosen a specific solution for the Laplace, so a specific right-hand side that gives me strong gradients on one side of the domain and basically a flat solution on the other side of the domain. So if I use my heuristics, I know that where the solution is basically 0, having a feature or not having, so having a hole or not having a hole must be the same, because in fact the solution is 0. If I put a hole, if I remove the hole, the solution stays 0. So it doesn't seem to change a lot. And I can test my estimator in this case. And in fact, the estimator for each feature tells me how important the feature is. So it tells me what is the bound on the error that is due to that specific feature. And in fact, what I discover is that for this solution, I need, if I want to bring the error down to 10%, I need to put 8 features in my domain, and those are the 8 features that matters. How do I know that they matter? Because I compute the estimator for each feature, and I just take the biggest one up to 10%, up to until I know that I reduce the error to down to 10%. So, and I can, in fact, what I can do is that I can introduce one feature after the other. So I compute the estimator, and then I can put the feature in sequence according to the importance they have, how big their estimator is, and then I can add it one by one, and I can study the behavior of the error and the behavior of the estimator. Again, you see that the error is the orange line, the estimator is the blue line, and the more I add the features, the more the error goes down, and the estimator together with the error in a very, really following the same trend. This is what really matters to us. Okay. So, yes, okay. Now, I basically, what I've been trying to explain is that, this is a kind of, the theorem that I've been discussing until now. So the theorem says that, if I have a collection of complex features that have been removed, and if I call U0 tilde the feature solution that is possibly extended on removed positive features via the bounding box, as I explained before, then the estimator that we have computed is an upper and lower bound for the error up to the oscillations, and the constants that are in between, so the constants that are hidden in these symbols are independent of the size of on the size of the different features. And so in the terms, say in the adaptive adaptive methods terminology. This means that our estimator is both reliable and efficient. And in fact, in all our experiments, we have seen that the efficiency index, that is basically the number, that the constant that is hidden in here, is relatively close to 1. It can be 1, 2, 3 maximum. So it's up to 5 in the very bad, say in the worst situation that we have experienced. So the effectivity index is in fact very very small. Okay. So now I want to move, say, to the second challenge that I want to discuss. That is the following. Until now, I have assumed that I know U0 or its extension U0 tilde. But in the reality, so in the real world applications, this is not true, of course, because my simplified domain is not a cube, but is still a complex geometry. So I don't know the solution, but I know a discretization of the solution. And sometimes I know a discretization of the solution on a rather coarse mesh, because it depends on how difficult the problem is. Sometimes I'm not given, say, arbitrary fine meshes to be able to compute the solution U0. On the contrary. So we want to understand whether the fact of not knowing U0, but knowing only an approximation of U0, destroys our theory or not. And on the one hand, and on the second hand, we want to know whether we can keep things under control and possibly balance the two errors. Okay. Okay, maybe I will. Okay, I will go through this slide, although it's I'm running a bit late. I'm sorry. So before doing that, I want to give you just a final example because I promised it in my outline. So this is again an example where on the simplified geometry I use very fine meshes, and you see I have all these features that I have numbered. So this is somehow a complex problem, and basically I compute the solution U0 on the simplified geometry. That is the solution due to a displacement of the top. So the top part of the domain is pushed on and rotated on a side, and then I can compute my estimator, and I get the features ranked according to the estimator. So these times the features are not ranked according to their size or shape as it is normally done in CAD systems, but now the features are ranked according to their impact on the numerical solution. And you see here that, for example, we look at the ones in red. The ones in red are 5. Yeah, these are the biggest one. So 5, 6, 7, and 8. And in fact, these are those ones are the holes in the stiffeners. So the stiffeners are these four triangles, thick triangles that are there to make the structure more stiff. And of course, if I drill holes in this stiffener, I get less stiff structure. And in fact, those holes are the ones that matters the most when I look at the error that I do, because the estimator is the biggest one. And then we can look at what else. So 9 is also very important. 9 is this little hole. Why it matters? Well, because it is in the part of the structure that bends. So the fact of having a hole changes it. Okay. So I will be a little bit quick on that, probably. Yes, I will skip this. Yeah, sorry, I skipped this. Okay. Now I go to the second problem that I want to discuss with you. That is exactly this one. So instead of having U0 now, I have U0H. This is my problem now, that I want to compare U with U0H and not with U0. So what do I do? Well, in fact, before I had a representation of the error that is like this, and now I can work a little bit and I get another representation of the error that is this one here. So where you see that now I have U0H and now this Laplace, you have to imagine that, yes, so I'm computing, say, regular enough solutions, or you have to imagine that this is just the Laplace in the sense of, I mean, it's the Laplace element by element plus the jump of the Neumann term on each edge of the mesh. It's the same. What is important is that I have basically a part of the, so in my representation, I have a part that is due to the residual of the discrete, so these are residuals, so it's how far is the Laplace of U0H from F, so is the residual of the continuous problem, and then I have this one is the residual on all the boundary that is not a feature, and this one is the error due to the simplification. So I can actually do the same. Here you see that I replace formulas with words. This very same representation can be written for general problems. Just formulas become very long, so I don't want to fill my slides with formulas. But again, these can be worked out. And in fact, once I have the idea is always the same. Once I have a representation of the error, I just go with Sobolev inequalities. So I need to do exact, Sobolev inequalities and track the constants for all these terms, and I get an estimate of this type. So the first term is the numerical error, and the numerical error that you see here is just the usual, say in this case is the usual residual error estimator that I have because I'm computing a discrete solution. But then, I have an extra term that is that is exactly the estimator we have just developed, because it's just, you see, it's just the same shape as before. So I can perform exactly the same Sobolev estimates that I did before to obtain the estimator before, and I get exactly again my, say, defeaturing estimator that I had before. Okay, so sorry, I'm going. Okay, so this is the case when I just use this representation and I go via Sobolev. Via Sobolev inequalities. This is somehow an whole technique for the numerical error. We can also decide to refine a little bit our numerical error. So our approach to the numerical error. Here I have written the residual, and then I proceed with Sobolev estimates. This is what is called residual-based error estimator for the discretization part that is exactly here. I can do a bit better. I could use equilibrated fluxes. So instead of representing things via the residual, I can represent things via the equilibrated flux. I don't think I will enter into these details, but just say the important message here is that the method that I present is actually compatible, can be used. So the defeaturing approach can be used together with say residual-based error estimators, and also with more sophisticated estimators for the discretization error, like the equilibrated fluxes. So I will jump through these slides. And I just want to present one numerical test to you before leaving the space for the questions. So imagine that this is the solution we want to compute. So this is the simplified geometry is a square. So we are still in very academic, still approaching very academic problems for the time being. So my simplified geometry is the square, and my complex geometry is the square minus this shape that, as you see, cut my mesh in a very generic way, just because I don't have a mesh of the complex geometry. And I can run a numerical simulation. Here you have to follow me. So here these are two different simulations. I can let the mesh size goes to 0, or I can let the size of the feature goes to 0. I have two parameters, so I need to run two different tests. The first one is the feature as a fixed size, but the mesh size goes to 0. So the feature has a fixed size, which means that the error due to the feature, that is the green one, stays constant because the feature doesn't change. And instead, the error due to the mesh, to the discretization error, is this one, so goes down. And now the total error, the real error that I do is represented by the red line. So it goes down at the beginning, and then it does stop going down, because at some point the error due to the feature matters. So the error is just stuck there and cannot go down. And this is well represented by our estimator, which includes both guys. So the discretization and the geometry error, that is the blue line. So you see that the blue line is actually above the red line and follows the same behavior. This is also true when instead I fix the mesh size and I vary the size of the feature. Again, here you see that the error is the red line, and the estimator, the complete estimator is the blue line, and then the other two are just the breakdown of the estimator. And you see that, again, the estimator is an estimator of the error, and in this case, the distance between the two goes to 0, and this is to be expected. Because in fact this is done via the equilibrated fluxes, that has the advantage that there is no constant in front of the discretization estimator. So if you want, the effectivity index is equal to 1, so it is normal that it actually goes to the two curves coincides. So I want to conclude via another test. So the last one that I'm presenting, I can use, so this is what I have. The error is bounded by a numerical guide. This can be estimated via residual based, in a residual based manner, or in an equilibrated flux manner. It doesn't matter. The discretization error can be measured by like this, and then I have a geometric error, the featuring error, that is measured via the estimator that I have been proposing to you. Now I can use this to run adaptivity, to run full adaptivity, in the sense that I can look at the error, and then at each step I can decide if I need to add a feature or if I need to refine the mesh. So if I do this on a problem that is similar to before, it's just that the features are a bit smaller than before. I can try to run my adaptivity, and this is what I obtain if I do it. So here I'm really saying I compute a simulation without features. I estimate the discretization error and the featuring error. I decide if I introduce a feature or if I refine the mesh. If I proceed like that, after 10 iterations of my procedure, I arrive here. So this is, you see that I have refined the mesh at sometimes, and I also have introduced a number of features. You see that the features are there. Okay, and then if I plot the result, this is what I obtain. So the orange results are the one where I forget about the feature. So it's the standard adaptivity, where I take my geometry as it was the real one, and I just run and I just look at the discretization error. Instead, the blue ones are when I introduce my geometric error. So I keep this into account, and I possibly introduce features. You see sometimes there are jumps, and the jumps are when I actually introduce the feature and the problem changes. Okay, So if I do that, I can look at these two. At the end of the day, I obtain, say, a new geometry with a given mesh that is supposed to provide me the best so the smallest possible error. And I can look at what are the difference between the two when I use the geometric, when I introduce the geometric error and I keep it into account, so the blue line, the blue one, or when I don't introduce the geometric feature, the geometric error, so I forget about it. So these are the two different meshes. This is the standard result of adaptivity from thousands of publications about adaptivity. If here I'm computing a solution that has a strong gradient on the left, is exactly the solution I proposed before. So of course the mesh is refined where the gradient is big and is not refined where the solution is zero. And this is the mesh that I obtain. If I also remember that I had removed all my features and I keep on adding them when needs be. So when the estimator tells me that I should do it. So in the left, the estimator that I have, I mean, when I compute the estimator is only the discretization estimator is 10 to minus 5, but the error is of order 1 because I forgot about my geometric features that were gone to start with. And instead, in this case, the estimator is 10 to minus 2, and we know that also the real error is 10 to minus 2 because I'm keeping track of all the different small mistakes that I do in my computation. So I want to conclude by reminding you that I've tried to use a mathematical approach to estimate the impact of geometric simplification on the analysis. And our aim is to provide the tool in the hand of practitioners to be able to control accuracy. All what I have done works on isolated features with natural boundary conditions, and we need to extend it to, in a more general way, to time-dependent problems, to other boundary conditions. I mean, this is really the beginning of a big, of a lot of research that can be done in this field. And I just want to conclude very, very quickly. So with a problem that I cannot solve with this theory. The problem is the following. The one that you see here is Switzerland, the country where I live, that has very complicated boundary because it's a mountain country. So the boundary are the peaks of the mountains. And so this is not, this is a complex boundary, but is not that I have isolated features, is everywhere complex. So how can I simplify this boundary with a given complexity? So imagine that I have a given number of degrees of freedom of, say, a given number of control points. If we speak about spline curves, how do I distribute? Can I distribute them in order to represent a simplified version of the country that still provides me a given control on the, I don't know, on the heat equation when I try to study the heat equation across the country? Can I extend the method to, say, everywhere complex geometries? Well, the method that I have introduced does not extend, and I can ask myself what I should do. And this is, I mean, we have ideas, but so it's just to say that this is not a problem we can solve now, but that I consider interesting. Okay, and with that, I thank you for your attention, and I apologize for being 2 minutes late.
Thank you, Professor Annalisa, for that interesting talk. Now we are open for questions. If you want to participate, you can raise your hand via the Zoom system, or you can write your question on the chat, in the chat. I want to ask you something.
Mm-hmm.
For example, in the conclusion you said where the form or the shape of the features matter, right? Maybe you have domains that with a strange boundary that you cannot do a geometric simplification. But is there a concept of a domain that can be that can be simplified. I mean, let me explain. If you have a definition of what on how is it the domain or some properties that the domain has to satisfy in order to apply the geometric simplification method.
Maybe I go back. What is it? So I mean the assumption that that we have is that features are isolated. So features can be holes or can be say or can be so in this case, for example, one thing that is very tough for the construction of the mesh are the fillet. So in the real life, objects are not constructed with sharp edges because sharp edges cut. So all the objects are constructed with fillets, so the corners are smoothed out. And if you want to construct a mesh for a smoothed out geometry, it requires a lot of tetrahedra to represent the curvature of the fillet. So now fillets are removed. From here to here, fillets are removed. And I can ask myself, is this important? And in fact, it is important because the sharp edges generate singularities that are not present in the geometries, in the simplified geometry. So in general, any sort of feature that is localized can be treated with this theory. And the theory applies to basically parabolic problems, to elliptic and parabolic problems, to saddle point problems. So the theory is very general. But then if I have the boundary of Switzerland and I ask myself, well, I don't want to use 1,000 degrees of, I don't know, 1 million degrees of freedom to represent the country, but I want to use only 100,000, how do I do? What do I remove? And this is not so easy to answer, I think. But it's
Okay, thank you, Professor. Nice. Just one more question is that the features has to be isolated, but maybe holes are when the features are convex is better or it
no,
does not affect at all.
It doesn't really matter, in fact.
Okay.
Now, one could try to develop, say, a more sophisticated theory, because here the assumption that we have is that features is isotropic in the sense that the length of the boundary and the diameter of the feature are comparable. So the feature cannot be extremely long, for example, okay? But so one could refine the theory in order to deal with anisotropic features. So to have the estimator, I mean, my estimator, if we look here, for example, my estimator depends only, I mean, I extract the length of gamma, so the length of the boundary of the feature. I could also extract as a parameter. In this, I could also try to track the behavior of the constants with respect to the diameter in case they are not comparable. And then I would get a more general theory that keeps into account other aspects of the feature. At this point, as soon as the feature is isotropic, everything works.
Okay, thank you, Professor, for that interesting talk. If we don't have any more questions, then just go ahead with the next talk. Thank you again for contributing here.
Thank you. Bye-bye.
Bye. We have now Professor Cristina Pignotti, right? Let me make you co-host. You can unmute yourself.
Thank you. You can hear
Hi,
me?
Professor. Yes.
Hi, thank you.
Thank you for being here. We will start in 2 minutes, but before that,
Okay.
I will ask you to try to share your screen.
Okay, 1 moment. Okay, can you see?
Yes.
We can also that's right. Can you see?
Full screen.
Okay.
Yes. Okay, I think we can start now. It is a pleasure for me to present Professor Cristina Pignotti. Is Pignotti right?
Yeah, right. Pignotti.
Okay, Pignotti. She's a professor of the mathematical analysis at the Department of Information Engineering and Mathematical Science at the University of L'Aquila. She earned her PhD in mathematics in 2001 from the University of Rome, with a thesis entitled Optimal Control Problems with Exit Time, Semiconcavity and Applications, under the supervision of Professor Canarza. Prior to that, she obtained a laureate in mathematics cum laude in 1994 from the University of Camerino, Italy. Professor Cristina Pignotti is recognized for her contributions to the fields of control theory, partial differential equations, mathematical models, and their applications. We're very happy to have Professor Pignotti here. Thank you for supporting our event with your contribution. And I hope everybody enjoyed this interesting talk.
Thank you. First of all, I thank for the nice introduction, and I thank the organizer for the kind invitation. So I will present some results recently obtained with in collaboration with my PhD student Chiara Cicolani and Elisa Continelli on multi-agent model. In particular, we consider first order model, so the so-called Exelman-Krause model, and the famous Fugger-Smale model, which is the second order version. And we add in the model time delay, which are natural in application, and a communication. We assume that we work with a non-uniform communication. I will explain later. Non-uniform interaction, sorry, and a possible communication failure. I will explain later what I mean with these terms. So you know that multi-agent systems have several applications in different scientific disciplines. You might think, for instance, biology, ecology, social sciences, economics, physics, engineering, robotics. And for this, they become in recent years a very active research field. An important feature that often we observe is the possible that is studied from researchers is the possible emergence of a self-organization leading the group to a globally collective behavior. You may think to a flock of birds, for instance. You see, they remain close enough and they tend to move with the same velocity. For this, we call this model as alignment models. Now we are interested in the so-called Exelman-Krause model, originally proposed in this paper of Exelman and Krause in 2002. Since then, several generalizations appeared. For instance, among the other, Canuto, Fagnani, and Tilly studied the PD version of such a model, and Joben and Moch studied the formation of cluster in case of bounded confidence. And also there are some control problems studied by Bonkev, Caponigro, and Borsi in a paper of 2015, and a more recent paper of Piccoli, Benedetto Piccoli, Anastasia Puradier-Dutel, and Emmanuel Trela. This is our model. So we consider a set of n agents. You might think to agents or their opinion, n greater or equal than 2, and we assume that the opinion or the agent are in the Euclidean space Rd, and the classical Exelman-Krause system reads in this way. So we have one equation for each agent, of course, initial condition, and this kind of equation That means that each agent adjusts its opinion, taking into account opinion of other agents. You see, you have in this sum, which is the derivative for xi, we have a term for each other agent. And in particular, there's a weight, a strength of this influence of the agent j on the agent I, which is typically in this form. So we have a function, typically depending on the distance among the agent, you may think, or among the opinion. Typically, this function is continuous, positive, and non-increasing, and it's also reasonable to assume that this function tends to 0 when the distance among the agent or among the opinion tends to infinity. And actually, in the originary model, ICMAM Krause consider a bounded confidence radius. So this means that this interaction strength are positive only when the agent J is sufficiently close to the agent I, so under a certain radius, confidence radius. On the contrary, here we consider this influence function always positive. And there's also a normalization factor, 1 over the number of other agents, so n minus 1. Since we have a sort of saturation, so we want that the total amount of influence on each agent is in some sense bounded. This is important, especially when you want to pass to the limit, to the mean field limit, and in order to approximate a system that can, the system that can be done of a lot of scalar equation, if we want to approximate it with a PD, but we will say something later. So as I said, that in the original model, P was a compact support, but here we deal with P always positive. So we define the diameter of the system in this way, so just the maximum between the maximal distance among two agent or two opinion. And we say that the system converges to consensus if the diameter tends to 0 as the time t goes to infinity. We will consider also the second order version of such a model. So now for each agent, we have a pair of vectors, xi and vi. And as usual, xi denotes the position, while vi is the velocity. And the standard Cooke's-Main model, so the model describing the formation of swarm of birds, flock of animals, reads in this way. So as usual, you know, the derivative of the position is equal to the velocity. While, so we have two equations for each agent. So the derivative of the position xi is equal to the velocity vi. And while for the velocity, we have the same structure that previous, you see, we have the same structure that we have here for the first order model. So we have each agent adjusts its velocity, taking into account the velocity of other agent. With a certain, each agent influences the agent I with a certain, depending on a certain strength. We call AIJ the mutual communication rates, which are in the same form that before. Of course, as a normalization factor, here I wrote 1 over n, but before 1 over n minus 1, but of course is the same. This is in order to keep bounded the total influence on each agent when the group is very large, especially when this is important when we pass to the mean field limit. So this model has been introduced originally to describe the formation of languages, and then to describe the flocking of animals, like swarm of birds, but in general group of animals or school of fish. And so now collective phenomena and also this model play an important role in many scientific fields, such as robotics, control theory, economics, social sciences. So here we have for the second version, we have for the second order model, we have two diameters to define. So the diameter in space, so which is the maximal distance between the position of agents, and the diameter in velocity, which is the maximal distance between velocity of agent. And in this case, we say that the solution tends to flocking, or one can also keep previous notation and say consensus, if the diameter in space remain bounded. So if the agent remain close during the evolution, and while the diameter in velocities tend to 0, so the agent tend to align their velocity exactly like we can observe for flock of birds or animals in general. So one of the natural extension for this kind of model, so both the first order model and the Cooker-Main model, so the second order model, is the analysis of time delayed interaction. Time delay naturally appear in application, in many practical problems in biology, as in social dynamics, economics, control problems. So it's natural to take into account the effect of a time delay in the evolution of the system, and so eventually in the formation or not of consensus or flocking. So this is natural, as I said, indeed each agent needs a certain time to obtain information from other agent, and also you may think a time delay like a reaction time. So the agent see other position, other opinion in the case of first order model, the velocity of other animals in the group in the case of second order model, but they need a certain reaction time in order to react, so in order to change its velocity according with the velocity of other agent. So the presence of a delay make the model more difficult to deal with, and since even a small delay can destroy some geometric features typical of the undelayed model. For instance, for a simple Egg-Selman-Krause model with always positive influence function, so always positive the coefficient Aij. And also, if we assume that the coefficients are symmetric, we can show that the system, it's easily to show that the system converges to consensus. Just for symmetry reason. But if we add a delay, then the symmetry is broken, and in turn the asymptotic analysis requires finer argument, and the problem become very difficult to deal with. Concerning the second order consensus model, so the Cooker-Main model with time delay, several results have been obtained in recent paper. For instance, Choi and Askovet and Choi and Lee deal with the first with normalization. This is a model with normalization, with normalized interaction strength. And also in the paper of Choi and Lee, and also the paper with Yonpil and myself, we deal with, we prove consensus results of flocking under smallness assumption on the time delay sites, also in the subsequent paper of Askovic and Markut, that they also consider a self-delay in this model. Then there's also a paper with my former student Irene Recche-Valerio, where we consider a model with Cooker-Main model with hierarchical leadership, and another paper with Emmanuel Trela, where we dealt with the general Cooker-Main model, but also, as in other paper, we need, in order to have our flocking result, we need to assume that the time delay is sufficiently small. More recently, there's a paper of Mauro Rodriguez Cartabia that finally proved for a Cooker-Main model with a constant time delay, the convergence to flocking independently of the size of the time delay. This technique has then been extended by my PhD student Elisa in our recent paper to the case of Cooper-Smale model in case of time-dependent time delay. So concerning the first order model, so the opinion formation model, in the case of time delay, analogously, the result convergence to consensus has been first proved for small time delay. I quote this paper, my paper with Jean-Pierre Choi and my former PhD student Alessandro Paolucci, and also a paper of Jan Askovec. Recently, in the spirit of a previous extension for Cooper-Smale, in a paper with Elisa, we generalized the previous argument, and we proved also for the opinion formation model convergence to consensus without a restriction on the time delay sites. Moreover, in this paper with Elisa, we greatly relaxed the assumption on the influence function. I will precise later on our assumption. So another scenario that can occur is the one in which the system particles suspend the interaction they have with other agent. So as a consequence, there's a lack of a connection between the agent. That is, of course, an obstacle for reaching consensus. So then it is important to find condition ensuring that indeed we have this alignment, so this consensus or flocking for a second order model. So also it may happen that the agent involved in an opinion formation are not able to exchange information with all other agents. In this case, we are in presence of a non-universal interaction. This means that the agent are able to influence only the opinion of the particle they are linked to. So to deal with this kind of interaction, we have to consider a graph topology over the structure or a network topology. And as in this recent paper on another multi-agent system, which is the Kuramoto model studied in these two papers. So a paper of Dong Ai Kim and a recent paper of Connor Carty, Jean-Pierre Choi, and my PhD student Chiara Cicolani, and myself, a very recent paper for Kuramoto. So here we are interested in studying consensus for solution to Eggsman-Krauss model, and also, I will say later, Cooper-Smale model with time delay, time dependent, and also pair dependent. So I consider several delay functions depending on the pair of agent, and non-universal interaction. So each agent influences not all other agents in the group, but only a subgroup, and a possible lack of connection. So, as I said, also the weight function that we consider to explain the communication failures are depending on the agent pair. So we have several weight functions, and they can degenerate. In this case, we have a loss of connection, not only among agents that normally are not linked each other, but also there is a gap in the connection among agents that typically are able to exchange information each other. So we will introduce a persistence excitation condition. This is the name in the literature for dynamical system. And under this condition, we establish exponential convergence to consensus when the network, so when the graph describing the interaction among the agents is strongly connected. This is done working with a very general influence function, and without requiring any smallness assumption on the time delay sides. Okay, so our result is very general and greatly improves previous works. I quote, for instance, this paper. and Choi Askovec and Choi Lee, Choi Paolucci, and myself, and a paper of Askovec, Bonnet Flaillac, a more recent paper with Elisa Continelli, where we just consider the first order model, and we assume that the weight which are responsible for the gap in the connection, for the loss of connection, is independent of the pair. And also a recent paper of Fabiancona, Mohammad Bentaibi, and Francesco Rossi, where also they deal, but I will explain later, I think, but they also deal with the first order model, and without any time delay, they prove consensus, but not exponential consensus. So I will present first our model, so things will be clear. So consider a set of n agent, n greater or equal than 2, and we denote by xi the opinion of the agent I at time t. Xi is in Rd, and our system is the following. So with respect to previous model that I wrote before, I wrote just the part in blue, except that what I call now B was A, but so now I add the time delay, which is which is a function depending on the time variable, and also I have several time delay functions, so depending on the pair. So this is tau ij is the delay in the influence of the agent j in the agent I. In general, it's good to assume that they depend on the pair, since you may have some agent more influential than other. So sometimes the influence of the agent J arrives almost immediately on the agent I, and sometimes it requires more time. And also is depend on the size of the time delay depend also on the reaction time of the agent I, in this case, receiving this influence. So the delay, and also we have, so the delay, we assume the function, the delay function, they are assumed to be continuous and just bounded, but tau, the bound, can be any positive constant, so we do not assume smallness condition on the time delay sides. The coefficient, the strength of the influence on the agent I are defined in this way. If you remember before, I wrote a function of C depending on the distance between the agent I and J. So now I can consider a very general function, so just a function of both arguments. Of course, the important case in the application remains always the case in which such a function depends on the distance, and since we expect that the agent closer influence in a stronger way the agent I with respect agent far. So the influence function is just a positive bounded and continuous. We call capital K the norm infinity, while the coefficient key ij appearing in the equation describe a network topology. So this coefficient is 1 if j transmit information to I and 0 otherwise. Also, I have to define this weight in violet, alpha ij. They can degenerate. So they are responsible for the loss of connection that can happen for certain times among agents that typically are linked. So this wave function also can depend on the pair IJ, while in this paper with Elisa, we consider the case where these coefficients are the same. So alpha is independent of the agent IJ. And also in this paper with Elisa, we don't consider the network topology. So we are in a situation all-to-all connection. So each agent is linked with the other. But of course, we can have a loss of connection due to this weight function that can also be 0, for instance, appearing in the equation. Okay, so in the previous paper with Elisa, we don't have this key ij, but there's a all-to-all connection, and this weight are equal to alpha of t, so independent of the pair. Also, I quote a paper of Ancona, Bentaibi and Rossi, where they also deal with the, they also consider this kind of weight function at ij, but they don't consider the network topology and nor the presence of time delay. And also, as in my previous paper with Elisa, they deal just with the first order model. And they obtain a weaker result since just they prove that there's convergence to consensus, but not exponential, what instead we obtain with Elisa. And so this condition, persistence excitation condition, is this one. So there are two positive constants, capital T and alpha tilde, such that this bound holds. So this means that the weight alpha ij has to be large enough, so the average has to be large enough on integral of length, on time interval of length capital tau. But capital T, but capital T can be large as you want, and alpha tilde can be small. Just we need this kind of uniform condition. Okay, so without loss of generality, eventually taking a smaller constant alpha tilde, we may assume that alpha tilde is less or equal than 1 over k. But of course, if it is not, I can substitute this with another smaller constant, so no problem with this. Note that this condition becomes relevant, so the problem is harder to deal with when T is large and alpha is small. In this case, the degeneracy is worse with respect to the case in which, for instance, we have this condition satisfied for a small t and for a large alpha tilde. Okay. Of course, this condition this model includes also the case in which we do not have the degeneracy. In such a case, the weight function alpha is 1, and of course, this condition is satisfied. So this result for this general model includes also previous result in the all-to-all setting. So due to the presence of the time delay, our initial condition are function as typically, so we have to define function as initial condition for each agent, and we assume that initial data are continuous function, and also we have to consider a graph topology over the structure. So we assume that we consider a D-graph with vertices and side, and we assume that the opinion of the agent are located at the vertices, and the agent interact each other via a network topology, I will say. So we assume we denote by Ni the set of vertices, so the set of agent that directly influence the vertex I. So this guy, and a path in a D-graph from E0 to EP is a finite sequence E0, E1, EP of vertices, such that each successive pair of vertices is an arc of G. The number of, sorry, cannot see my. So the integer p is called the length of the path, and if there's a path from I to j, we say that the vertex j is reachable from the vertex I, and we define the distance from I to j with this notation as the length of the shortest path from I to J. So I and J have a distance, for instance, 3, if the path for reaching I from J is requires 3 passages. So we assume that the D-graph is strongly connected. This means that each vertex is reachable from any other vertex, and we define the depth of the gamma that we denote with gamma, sorry, the depth of the D-graph in this way, as the maximal distance among 2 vertices. And so any particle can be connected to the other individuals via no more than gamma intermediate agents. So this means that each agent can influence any other agent with a certain intermediate passages, so influencing other agent, and the path has a length, each path has a length less or equal than gamma. Of course, we have that the length of the path of each path is less or equal, so the depth of the graph is less or equal than n-1, where n is the number of agents. And since we assume that the D-graph is strongly connected, the gamma is greater or equal than 1. So each agent can be reached via gamma intermediate passages to other agents. So we need, in order to prove our convergence to consensus result, we need some preliminary estimate. And we have to introduce, since we will work in specific time intervals, so fix a vector v, any vector v, and fix n, a natural number. We define this interval in of length tau, where tau is the upper bound on the time delay functions, and gamma is the depth of the D-graph, and T, capital T, is the time appearing in the persistence excitation condition. So we will work in interval of this type, and we need to introduce this quantity MNV and capital MNV, which are minimum and maximum of this scalar product in such interval, and varying the index I on the set 1n. So we have xi are the agent, the agent in the group. So also we will need to consider other 2 quantity for each n and each vector v, which is now I have to consider the minimum and the maximum of the scalar product at the right end of this interval in. So this is our lemma, which obtained with Chiara and Elisa, generalizing previous result with Elisa. So for each vector, we have that this scalar product for each agent is between M0V and capital M0V for all time, where according with the previous definition, you see if here I consider n equal to 0, just the interval in becomes the interval I0, which is just, if n is equal to 0, is just the interval minus tau 0. Okay, so M0V and capital M0V are the maximum and the minimum of this scalar product in the interval minus tau 0. So here we are looking to the initial conditions, since we are in the negative interval minus tau 0. So then we can show that the scalar product for each agent for all time remains between these 2 quantities. To prove this, we can argue by contradiction. Of course, this inequality is satisfied. So I want to prove that these inequalities are satisfied for each t greater or equal than minus tau. Of course, by definition, this inequality is satisfied in the negative interval minus tau 0, since these are M0V and the capital M0V are just the minimum and the maximum regarding the initial condition. And so we fix epsilon positive, and we denote k epsilon, the set of the time for which this maximum remains less than capital M0V plus epsilon. So I want to prove this second inequality. So this condition is satisfied in the negative interval minus tau and 0, and I call k epsilon the set of positive times such that this inequality holds, adding here epsilon. And we denote as epsilon the supremum of such a set. So by continuity, we have that this set is non-empty, and then S is positive. We claim that S is plus infinity, this supremum. In fact, suppose by contradiction that S epsilon is bounded, and then of course in the interval 0 S epsilon such an inequality is satisfied, and if S epsilon is finite, when I pass to the limit, then I have the equality here. And now I want to have a so I want to reach a contradiction. So we consider our equation. Of course, in the equation I have a delay, and since t belongs to, I consider this equation is our equation in the interval 0 S epsilon, which is S epsilon, the supremum of such a set k epsilon, where I have such an estimate. And of course, t minus tau ij belongs to previous interval minus tau S epsilon. And then also this delayed state satisfies this estimate. And so one can estimate, using also the fact that this factor appearing in our equation, these guys are less or equal than 1, I can estimate in this way our equation. Okay. So now I can apply Gromval inequality, and using the fact that here, of course, the initial condition is less or equal than capital M V naught by definition, since capital M V naught is the maximum of such a scalar product in the whole negative interval. So in particular is greater or equal than this guy. So we have that this scalar product is less or equal than this guy. And this gives a contradiction, since for all t in 0 S epsilon, we have this, and then passing to the, also for all agent, then considering the maximum and passing to the limit, we have that this inequality has to be satisfied, while we assume that S epsilon is finite, and then we want, when we consider the limit as t goes to S epsilon, we want the equality, the identity here. On the contrary, we have that the scalar product remain strictly lower than this guy. So this means that the supremum of previous set is infinity, and then this inequality holds for all time. And since epsilon can be any positive constant, this means that the scalar product remain for each agent and for each time remains less or equal than the maximum of the scalar product among xi and v in the negative interval minus tau 0. To obtain the other inequality, since you remember in the statement we have two estimates from above and from below, to obtain the first inequality, we just instead, I just work with the vector minus v, and so minus xi v is equal to xi minus v. So I can apply the second estimate, so the one proved, and so I can, using that, the maximum of the scalar product with minus V is the minimum minus the minimum of the scalar product with V. We have also the other, we proved also the other inequality. This result can be refined in this interval. So we start with this estimate that holds for all time greater than minus tau, so in particular for all positive time, while in such an interval where you have to take into account the network topology, so gamma is the depth of the graph, I use the persistence excitation condition, since this capital T is the size of the integral in order to have that the weight is sufficiently, the average of the weight is sufficiently large, so larger than a uniform positive constant, and tau is the bound on the time delay. In such an interval, I1, I can refine previous estimate, obtaining this estimate here. So before I didn't have this term with gamma. Gamma is a suitable positive constant. Before I just had xi scalar product B greater or equal than m v0 and less or equal than capital M v0. So now I can refine this estimate. This is the very key, these are the very key estimate in order to prove our result, just very technical, since in order to improve so previous estimate, we have to carefully analyze the trajectories of the solution of our system, starting on a suitable trajectory, since we have the delay, we have to take into account the initial data, which are function, and we have, so the integral has to be, the interval has to be, so we have to move enough in order to use the persistence excitation condition. And so finally, after careful estimate of the trajectory and also using some the network topology and some Grombahl inequalities, so one can have this estimate. So one can reproduce our argument in the successive interval IN. So one can move, if you remember, I started with the introduction of a sequence of time intervals. So this, they are interval of length tau, if you note, but we move with the growing, and we move in the positive outline. And sorry. And so reproducing and refining this argument in successive intervals, time intervals, so finally we obtain our results. So if I recall the influence function has to be positive, bounded, continuous, the time delay continuous and satisfying this bound, the graph has to be strongly connected, so I need to reach each agent starting from any other agent, eventually through certain intermediate passages. The weight function has to satisfy the persistence excitation condition. Then we can show that under this assumption, every solution satisfies this exponential decay estimate. You see in parentheses, we have something depending only on the initial data, since here I consider the maximum with R and S in the negative interval. And here I have this exponential decay. We consider also the second order model. As you see, the structure of the equation for the velocity is very similar to previous one, but now the strength are depending on the position and not in the velocity. So the analysis is much more difficult with respect to previous one. And in fact, the previous paper that I mentioned deal just with the first order model. So it's not easy to extend the argument to the second order model. So our setting is, except that now we deal with the different model, the second order model, our setting is the previous one. So the delay function depends on depend on the pair. We have the coefficient Kij describing the network topology. We have the weight alpha ij, which are responsible for lack of connection, and also among agents that typically are linked. So for agent, for instance, such that this coefficient K is for agent ij, for which this coefficient is 1. And why the strength? So the strength or the influence of the agent J on the agent I is now less general, since the problem is more difficult to deal with. We have to pay with less general influence function. But as I said before, this is the most important case in the application, since typically each agent is more influenced from agents which are closer. So here we have the influence function that we call psi tilde, that depends on the distance between position of the agent. So the equation, this kind of the equation is for velocity, while the coefficient Cij involve the position. So for this model is more difficult with respect to the previous one. We call K tilde the norm infinity of this function K tilde, and as before, you have to give as initial condition, you have to assign a function, so now 2n function for both position and velocity. And we recall the definition of the diameter in space and in velocity. And as we said, asymptotic flocking means that the diameter in space remain bounded during the evolution, while the diameter in velocity tend to 0. This is our theorem under previous assumption on the time delay, on the weight function, and on the graph. If the function phi tilde is positive, bounded, continuous, and it satisfies this condition, then we have asymptotic flocking. So the diameter in space remain bounded, while we have an exponential decay for the diameter in velocity. Of course, as before, note that this quantity in parentheses just depend on the initial data. Just a comment on this assumption. Look here, gamma is the depth of the graph. So in the case of all-to-all, so in the case of all-to-all connection, so each agent is immediately influenced by any other agent, and it influences any other agent. We don't have gamma, so gamma is 1. And if the function phi tilde is decreasing, as in previous literature, this is, but I have another slide. So if this function is non-increasing and the interaction is universal, so as I said, gamma, so the depth of the graph is just 1, then the condition, our condition on the influence function reduces to this 1, which is the classical assumption in order to prove unconditional flocking, so flocking independently of initial condition. For instance, I quote pioneer papers of Hein Liu, Hein Tadmor, and more recent paper, this first two paper without any time delay, and more recent paper by Yong-Fil Choi and Jan Askovec, and myself with Emmanuel Trelat, including also time delay. And so we, in all this paper and also in a lot of other papers that I cannot mention here since there's a wide literature on Kugel's-Mann model. So in order to have unconditional flocking, so flocking independently of the initial condition, this is the assumption. So our assumption is this one under the classical assumption, so psi tilde non-increasing and all-to-all condition, so gamma equal to 1. While in a recent paper, Elisa, my PhD student Elisa Continelli, studied the Kugel's-Mann model with time delay, time variable time delay, and generalizing the influence function, they considered this function of phi tilde not necessarily monotonic, and then the condition become this one. So without the gamma, since ELISA considered the case of all-to-all connection. So without the gamma, this is the condition of ELISA, extending previous one and reducing to previous one, so to the classical one when we have the monotonicity of the field. So we generalize the model. Also, we have the network topology. So this is the best condition. So the weaker assumption that we need on the influence function in order to hope to have unconditional consensus as we found indeed. Okay. And so I emphasize that our paper is very general and improves previous work since they deal with, except the paper with ELISA and also Bonnet-Playac deal with the second order model, but they don't consider delay, they don't consider the network topology, and also they don't prove the exponential consensus, but just asymptotic convergence. In this paper I already mentioned, and there's a paper of Ancona, Bentaidi, and Rossi. They deal with just the first order model without any time delay, and also they don't prove in this paper exponential convergence to consensus. And also our paper is also more general than the subsequent paper by the same author, since here in this second paper they deal also with Cooker's mail, but without any time delay, and also then in the second, for the first order case, here where they give exponential decay, but for the second order model not. So our result is very, very general. Okay, so I skip this discussion. And just so I have some other structure studied in collaboration with Chiara Cicolani and Badis Wahab, a PhD student visiting L'Aquila some months ago. And so since I'm a bit late, just I want to skip to some extension and future direction. So changing sign influence function can be considered. We have a paper with ELISA. So the influence function can be, in this paper with ELISA, this influence function can be positive in some time interval and negative in other. So we obtain under some sufficient condition, we obtain consensus and also flocking for the second order model. And there's also a collaboration ongoing with Emmanuel Trela, where we are dealing for other behavior, not necessarily convergence to consensus, but for instance, convergence to some periodic solution, for instance. And control problem, one can study. I mentioned recent result for ICMAM model, and also a more quantitative analysis that can be useful in particular for the application of multi-agent model. And also something can be done concerning the PD model. So when the number of agents is very large, instead to deal with a system of very large number of ordinary differential equations, can be useful to work with the PD. And I skip the PD formulation for the case of the classical Eggsman-Krause model, but so I will go just to the further direction. So the PD analysis in the case of two or more population with delay in the interaction has not been done yet, except this result of Fornacier, Piccoli, and Rossi in the case of a model with leadership, but they just study well-posedness and control property, not consensus, since they don't have they don't have their uniform estimate that are crucial in order to study the consensus for the related PD. There's an ongoing project with Yong-Pil Choi and Chiara Cicolani, and also it's open the PD analysis in case of a changing sign influence function, but this we will approach this this topic. So after that, we will have more clear the situation for the particle system. So for the ODE model that we are studying, so we have some result with Elisa, and we are studying with also with Emmanuel Trellat. So there's a lot of direction that we can follow. Okay, I stop here. Thank you. Sorry for the delay.
No, no problem. No worries. It's okay. Thank you, Professor Pignotti, for that interesting talk. We're now open for questions. You know how to make a question. You can write it in the chat or use the Zoom system to raise your hand. I'm going to begin with a question. I want maybe I have no clarification of the PE condition because I don't get it intuitively. And I want to ask how restrictive is that condition, the PE condition on the functions alpha ij.
So this is natural since one moment, I come back to the model. Here, if for instance this function, so maybe it's easier to work with the first order model. Okay, so here if you have that, so this coefficient alpha ij can be also 0. So here if you have always 0, this means that just the derivative of each xi is 0. So essentially each agent keeps its opinion. So you cannot have a consensus. Okay. So you need some condition. So of course, if alpha is very small, you need that more time to influence for each agent to influence in a significantly way other agent. So this is a natural condition that is a condition like this is necessary.
Okay,
you mean so T can be large as you want, but we need a uniform. So we want to avoid that to reach a minimum of influence alpha tilde. You have to enlarge without any bound the time interval. So we have a fixed time, capital T, that can be also very large, such that if you consider such a weight in this eventually very large interval, you have that the influence is at least this can be small as you want, but you need a bound. So this cannot become a 0 with growing T, with moving T along the real alpha line, and T has not to become, to increase to infinity in order to have such condition. So this is a uniform bound that can be also very weak, which is necessary to have our result.
Thank you, Professor. Very clear. Okay, I think we have no more time for questions. There's another question by Luis Yapu.
The controllability result. Yes, thank you. That so I tried to say everything, but finally maybe. Yeah. So anyway, we have a paper, and so I arrive here. So we have a leader. So we have for other agent, we have for the other agent, we have the classical opinion formation model, except that we use a different name for the influence of the leader. So we have a leader, which is Y0, and other agent xi, x1, x2, xn. So just this is the Eggerman-Krauss model that I mentioned before, and I used a different name for the influence of the leader on the other agent. On the contrary, the leader is not influenced from other agent, but it follows a certain control law that can be his strategy or can be an external influence on the leader. And so one can show that, of course, we can put a delay in the interaction, and one can show that, I don't know, I don't remember if I brought the theorem. Yeah. Okay, so we consider this system and we fix X bar any point in RD, which is the target for the leader. So the leader has this aim, X bar, and he can choose the strategy in order that so the leader reaches X bar in finite time. And also we have such an inequality. This is the distance among the agent, and also I consider the distance, so I missed to define the distance. So this is the distance, so the maximal distance among agent, including the leader. So if this goes to 0, this means that also the distance of other agent with the leader goes to 0. So the leader reach the agent X bar, and also other agent when t goes to infinity, since the distance with the leader tend to 0. So you can reach any point X, any desired state X bar, which is the aim of the leader, with a suitable strategy U. So this is our result. But of course, concerning the controllability property, there's still a lot to do, since we have just a few results. For instance, you can study some optimal control. You can ask if there's a control that reach the target, such that the system reach the target in a minimal time, or minimizing certain function, for instance. Or you can consider the case with the 2 leader, 2 control, so a lot of problems.
Okay, Professor Pignotti, thank you again for joining us today.
Thank you.
We are having the next talk
Hi,
by Cristina Urbani. Let me make her co-host in order you to say hello to. Okay.
Hello,
Hi.
everyone.
Hello, Professor Cristina.
Hello. Can I share my screen?
Just a little second, please. We have Professor Andrés Rivera from the Universidad Javeriana. He's in charge today in the morning to the in-person part. So he's in the auditorium, and I want him to present, to introduce your talk. Just let me see if I can. Andrés, you can open your mic.
Yes, you can hear me. Right?
There's a little.
You can hear me?
Yes, I can hear.
Can you hear me?
Yeah.
Yes.
Yes? Okay. So, okay. Well, some few words before the talk about the Professor Cristina Urbani, right?
Yes.
That's correct. So let me introduce some for the audience for the Professor Cristina. The Professor Cristina Urbani is a research fellow at the University of Mercatorum. She obtained a bachelor's and master's degree in mathematics at the University of Rome Tor Vergara. That's correct?
Right. Yeah.
She also obtained a joint PhD from the Grand Sasso Science Institute de l'Aquila at the Sorbonne University in Paris in mathematics, in natural, social, and life science. Right, that's right?
Yes.
So thank you, Professor, for joining us in this conference, with the talk bilinear control of parabolic evolution equations. And
Yeah.
once again, thank you for being here with us, and the audience is yours.
Okay, thank you. So I'm going to share my screen. Oh. Can you see it?
Yes.
Okay. So first of all, let me thank the organizers for the kind invitation. It's a great pleasure and an honor for me to be part of this conference. So my talk today will be about results of control theory for parabolic evolution equations when you use a special kind of control, which is called the bilinear control. So I cannot change the slide here. So this will be the outline of the talk. First of all, I will give an introduction to the topic, and I will explain the main result we have obtained for controllability and stabilization of parabolic equation to some particular trajectories, which I will call eigensolutions. Then I will show you an application of such result to a degenerate parabolic equation. And then I will move to controllability of parabolic equations on network structure. And if I have time, I don't know, I will also touch results of controllability of the Fokker-Planck equation. So let me start. So here we have a control system, which is just a dynamical system in which the dynamics is described by a function of u, the state, and another function p, which is the function that you can choose in order to steer the solution of your PDE to a desired state. So in this talk, I will be interested in the notion of controllability along a trajectory. So first of all, what is a trajectory? Trajectory will be just a solution of our problem if you are given an initial condition u bar naught and a given control p. So our solution will be just, our trajectory will be just a solution of our PDE. And this control problem will be called controllable along this reference trajectory if for any epsilon there exists a delta such that if you pick an initial and final state in a neighborhood of the radius delta of the initial condition of the reference trajectory and the final in a neighborhood of the final trajectory at time capital T, you are able to find a control P, which is close to the reference control in some space, such that if the solution of your control problem that starts in U naught with control P at time capital T reaches exactly the desired state. So this will be the notion of controllability along a reference trajectory. So you can have different kinds of control system. We have boundary control system if the control, the function that you can pick is the boundary term. You have locally distributed control system if the control acts in a subset of the domain as an additive force. And then you have the third kind of control system, which are multiplicative or bilinear control system if the control is a coefficient in your equation. So this means that the control multiplies the state. So which is the difference between this kind of control system? But the main difference between this control systems is that the map from the control to the state is linear in the first two cases and non-linear in the case of bilinear controls. So this means that one cannot use the theory that has been developed for linear control systems, for instance, the duality between the observability and controllability, the Hilbert uniqueness method, and so forth and so on. So for treating this kind of control system, you should do something else. Moreover, there's another obstruction in trying to prove local controllability along a trajectory, which is inside this well-known theorem by Ball, Marsden, and Slamrod, which tells you that under very general assumption on operator A and B, meaning that for A, I just wanted to generate a strongly continuous semigroup, and B is just a linear bounded operator. So under this very common assumption on A and B, you have that the reachable set from an initial condition as a dense complement. So this means that this kind of controllability results have not hope to be proved for this kind of control problem when A and B satisfy this hypothesis. So in the literature for hyperbolic problems, what the authors have done in order to prove some controllability result along trajectories is to violate one of the hypotheses encoded in the result by Ball, Marsden, and Slamrod. And in fact, you can see that there are results of controllability along trajectories for the Schrödinger equation, for the wave equation, and so forth. But the spaces where controllability are proved are more regular, and in fact, the operator B is not bounded in this space. So here, there is what people have done for parabolic and hyperbolic problems. Sorry, but this machinery does not work for parabolic problems because what these results are based on an inverse mapping theorem and certain point of the proof, which does not adapt to parabolic problems because of the regularity of the space. And also, the big difference between parabolic and hyperbolic, as you know, is that the parabolic problems are not time reversible. So for parabolic problems, you should do something else. So you cannot prove this kind of controllability, but what you can do is to try to prove this kind of controllability on the reference trajectory. So you don't want to cover an entire neighborhood of the reference trajectory, but you want the time capital T to be exactly on the reference trajectory. And this is something that can be done because we do not violate the theorem by Ball, Marsden, and Slamrod. Okay, so let me set the problem. So now we will consider in a separable Hilbert space this kind of control problem by linear, because you see that the control will be the scalar input control P, which depends only on T. And so it has a very weak power on the equation. So A, for me, will be just a linear, densely defined linear operator, which is self-adjoint, accretive or quasi-accretive, like in this sense here, with a compact resolvent. So you know that under this assumption, we have a basis of eigenfunction of our operator A, and the eigenvalues can be ordered in an increasing way and tends to infinity as k goes to infinity. B, for now, will be just a linear bounded operator. And the reference trajectory we are going to consider are the so-called eigensolutions, which are just the solution of the free problem when you have p equal to 0, and the initial condition is the jth eigenfunction of the operator A. Okay, this will be my reference trajectory. Okay, so let me introduce this notion of general controllability for the pair A and B. So the pair A and B will be called general controllable in time t if there exists a constant, the best one will be called the control cost, such that for an initial condition, why not, this linear problem, let me stress the fact that this is a linear problem because the operator A is not be applied to the state, but is applied to the jth eigenfunction. So for an initial condition, this problem can be steered to 0. So if for initial condition, this problem is null controllable, and the control, the L2 norm of the control is bounded by the control cost times the norm of the initial condition U0. So I will be given two operators. These are called general controllable if this linear system is null controllable with a control bounded by the control cost times the initial condition. So it turns out that this requirement on the operator A and B is enough not for proving controllability to a reference trajectory, but something similar, which is the super exponential stabilization of our bilinear control problem to the eigensolution. So this means that if the pair A and B is generally controllable, then in a very short time, with a double exponential rate of convergence or super quickly, you can get really close to the eigensolution. But you cannot reach it exactly. What is missing is something on the control cost. In fact, if you have your pair AB, which is general controllable, and the control cost can explode in 0, but less than an exponential of C over tau, for tau small, then you are able to prove that the time capital T, the solution reaches exactly the eigensolution by using a control in L2. Okay, so everything boils down to proving AB general controllability. So we have given a sufficient condition for general controllability. And the sufficient condition are the following. Your operator A must satisfy the hypothesis I've shown you in some slide before. So self-adjointness, accretivity or quasi-accretivity, and compact resolvent. Moreover, you want a gap condition on the eigenvalues. This means that the square root of two consecutive eigenvalues must be bigger or equal to a uniform constant A. So here I put minus lambda 1 because we have seen that the operator can be quasi-accretive and so having some negative eigenvalues. So here, in order to have everything positive under the square roots, we put a minus lambda 1. Okay, so a requirement of the gap condition is that this the square root of two consecutive eigenvalues is bounded by a constant which is uniform with respect to k. And for B, we want that all the Fourier coefficients of B phi j, if we are looking for controllability to the j eigensolution, are all different from 0, and also you require these cities to be convergent. Under these assumptions, so gap condition and an assumption of the operator A that spreads the eigenvalues j in all directions, so all the Fourier coefficients must be different from 0, you have AB general controllability. But this is enough to prove super exponential stabilizability. If you want also to prove exact controllability to the reference trajectory, you want also something on the control cost. And so we have proved that if you have your operator A satisfying the gap condition and the operator B satisfying this stronger assumption, so you want all the Fourier coefficients be different from 0, but also bounded from below by a constant time, a negative power of the eigenvalue, then you have AB general controllability and also the control cost that behaves in a nice way, meaning that near to 0, it can explode, but less than an exponential of a constant over tau. So if you want to apply our result of super exponential stabilizability of controllability, you just need to prove these sufficient conditions. And in fact, I want to show you an application to a degenerate parabolic equation. So here we have this degenerate equation. It is degenerate because the diffusion at x equals 0 vanishes. And so here our operator B will be just the multiplication operator by this function x to power 2 minus alpha. At x equal to 1, we take a Dirichlet condition. In x equal to 0, when we have the degeneracy. If the degeneracy is not too strong, meaning that alpha is between 0 and 1, we can take Dirichlet boundary condition. Otherwise, if the degeneracy is strong, meaning that it's between 1 and 2, you are forced to impose a normal kind of boundary condition. Okay, so if we define this quantity, nu alpha and k alpha in this way, it is possible to prove that the operator A, the degenerate operator, is a self-adjoint active operator with compact resolvent. So the first assumption on operator A are satisfied. And also you have that the eigenvalues of your operator A are given in terms of the zeros of the Bessel function of first kind and order nu alpha. And the eigenfunction themselves are given in terms of Bessel function of order first kind and order nu alpha. So you have also an explicit formula for eigenvalues and eigenfunction. So what we want to check now is the gap condition on the eigenvalues, because it's the second requirement that you need on A to have the AB general controllability property. So if you look, for instance, in this book, there are some estimates of the zeros of Bessel function, and you can deduce a gap condition between the consecutive eigenvalues in the weak degenerate case and also in the strong degenerate case. So also the gap condition is satisfied. Finally, what you want to prove is the assumption on B. So you want that all the Fourier coefficients are different from 0 and bounded below by a negative power of the eigenvalues. And this is possible, and it is written in this paper with Pier Marco Cannarza. So this means that we have proven all the assumption we need, all the sufficient condition in order to have AB general controllability and the control cost that behaves in a nice way. This means that you're able to prove that our degenerate parabolic problem was locally controllable to the first eigensolution, because here we are looking at the Fourier coefficient of B applied to the first eigenfunction. So now one can think that how we can find operators B of multiplication type that verify the spreading assumption. So this assumption here, and this you can find this an algorithm in order that that build operator B, mixing coupling potentials that satisfy this kind of assumption on the eigenfunction. So now if you think to the gap condition, if you want to prove controllability to trajectory for parabolic problems, you see that one of the assumptions that we gave is the gap condition. And the gap condition, in fact, restrict the applicability of our result to one-dimensional problems. And so this is why we thought to apply our result in a special geometry, a special of the domain, which is a graph, a network structure. Because if you think what is a graph, is just a union of sub-nodes or vertices which are connected by edges. So it's like if you have the union of one-dimensional domains. So here, let me say some words on graphs. So here we have a number which is associated to each vertex, which tell you how many edges are shared by the node. And so we have external vertices if they are touched just by one edge, and internal vertex or nodes if this n of v is strictly bigger than one. So if the node is shared by more than one edge. And it is possible to define a compact graph that for me will be a graph with a finite number of edges with finite length. And you can also give a metric to a graph, just parameterizing each edge by a coordinate that goes from 0 to the length of the edge. And so it is possible to define functions on a graph, which will be just n-plet, and each component will be a function on an edge. And you can define a Hilbert space, the Hilbert space L2 on a graph just by considering the L2 spaces on each edge. And you give this definition of the scalar product which will be just the sum of the scalar products of each the components that are referred to an edge. Now we have to define what does it mean the derivative on a node, because on the edge, or the inside of the edge, the derivative is just the usual one-dimensional derivative. But on a node which is shared by more than one edge, you have to define what does it mean the derivative. And there is this rule that if the node is the initial point of the edge, you put a plus with the derivative. If it is the endpoint of the edge that is touching this node, you put a minus, and then you sum every contribution of the derivative that comes from every edge. So this is the definition of derivative on one internal node. So here you can build a self-adjoint Laplacian on a graph. You just need to define the function on the domain of the graph, the domain of the Laplacian on the graph. So we have Dirichlet boundary condition if every function and on the external node is equal to 0, so classical definition. And you have Neumann boundary condition if every function in the domain of the operator on the edges that are external have the derivative equal to 0. And also we need to define the let's say condition on the internal nodes, and we put the most common one, which are the Neumann-Kirchhoff condition, which tells you that every function in the domain of the Laplacian must be continuous on the internal nodes and with the derivative equal to 0. The derivative in the sense that I described before. So the contribution of the edges that have this node as initial condition will have a plus. The contribution of the derivative from edges that have this node as an endpoint will be with a minus. And therefore, you can define a Dirichlet Laplacian, a Neumann Laplacian, or Dirichlet Neumann Laplacian if on the internal nodes you have Neumann Kirchhoff, and on the external node you can have all the vertices have Dirichlet condition, or all the vertices are external vertices have Neumann condition, or both. In all these cases, you have that the Laplacian on a graph is a self-adjoint operator with compact resolvent. So this is nice because these are the conditions we are interested if we want to apply our abstract result. So now we have to look for the gap condition. So in fact, the operator, the eigenvalues of the Laplacian, Dirichlet-Neumann Laplacian on a compact graph verify this gap condition, which is not precisely what we need, because here we have a gap condition not between two consecutive eigenvalues, but between blocks of eigenvalues. Okay, so here you have a uniform gap condition among blocks of eigenvalues, because here you see an m and not one. So this is not really what we need. Something similar, so a uniform gap condition, but between blocks. We also have proven that if you have special graphs, like for instance the tadpole, the two-tailed tadpole, the double ring, or the star graph, if the edges are linearly independent over Q and the ratios are algebraic rational numbers, then you have a gap condition between consecutive eigenvalues, but this gap condition is not uniform, it's decreasing with K. So you see, we have two kinds of gap conditions, but that are not exactly what we need in order to directly apply our abstract result. So we have a gap condition, a uniform gap condition between blocks, and a decreasing gap condition between consecutive eigenvalues. So here it is natural to try to understand where we use this gap condition, why it is important. And in fact, the gap condition comes into play when we want to prove the AB general controllability of the operator of this of our equation. In fact, when you want to prove the AB general controllability, what you want to prove is that this linear system is null controllable. This means that at time capital T, you want to find a control P such that the solution reaches 0. And if you rewrite in terms of semigroups of this requirement here, this is equivalent to writing this equality. And then if you use the fact that your eigen function form a basis, you can rewrite this equality in this way. And if you recall that the eigenvalues are orthonormal, you can write this equation in this way. For each direction, you have an equality. And so in the end, you want to prove that there exists one control P which satisfies an infinite number of this kind of equality. If you rewrite a bit better this equality, so you divide by b phi j phi k, and we can do it because we know that these are all different from 0. If you divide and you define this sequence dk, then you want to prove that there exists one control P which satisfies these equalities, which are called moment problem, and this is called the moment problem. So what are the machinery that one usually uses to solve a moment problem? So now I have to introduce the notion of biorthogonal sequences. So two sequences in a Hilbert space are called biorthogonal if the scalar product is equal to the Kronecker delta. So why I have introduced this notion? In fact, if you have a biorthogonal family, which is biorthogonal to the family of exponential that I have here, and you define your control in this way, so this coefficient here times the member of the family, and you plug this function inside your equality, in fact, you have that this kind of control satisfies all these equality. So you have to prove two things. First, the existence of a biorthogonal family, and second, that the definition of the control makes sense, meaning that it is in L2, a function in L2. So here we can use a result by Canarsa, Martinez, and Van Costenoble, which tells you that if you have a sequence, non-negative implicit sequence lambda k, and you define the sequence of exponential in this way, then if you have a uniform gap condition between consecutive eigenvalues, then they ensure the existence of a family which is biorthogonal to the family of exponential, and also they give you all, a bound of the L2 norm of the members of the family in this way. So here you see where the gap condition appears when you have to solve a moment problem. So the problem is now that we don't have this kind of gap condition. We have other two kind of gap condition. And so what we have done with Canarsa and Alessandro Duca is to extend the existence result of a biorthogonal family in the case in which you have this sequence of non-negative real numbers which meet these two kind of gap conditions. So you have a uniform gap condition among blocks of eigenvalues and a gap condition between consecutive eigenvalues, which is decreasing. So you see that inside the blocks, the eigenvalues tends to shrink, to condensate, okay? But in any case, if you have these two kind of gap condition, we can ensure the existence of a family which is biorthogonal to the family of exponential, and we gave also a bound on the L2 norm of the biorthogonal sequence. So this means that we are able to solve a moment problem in the case of a tadpole, a two-tailed tadpole, a double ring, a star graph, because I remember you that the first gap condition is satisfied for any compact graph. The second one, we proved that this kind of graphs satisfy this requirement if the lengths are linearly independent of a Q and the ratio are algebraic irrational numbers. So this means that if you are given a compact graph and you assume that the weak gap condition is satisfied with this sequence AK, which goes like 1 over K to some power P, and you have your operator B, which satisfies that all the Fourier coefficients are different from 0 and bounded below by a negative power lambda K, then your bilinear equation is controllable on a graph structure by a contour which is in L2. And you can see your solution to the solution of your control problem to the related J eigensolution fixed J. So this means that we are able to control a bilinear heat equation on this kind of network structures. So the tadpole, two-tailed tadpole, a double ring, and a star graph. So let me spend a few words on the possible application of our problem, our control problem. So here from this paper, you know that the current that flows inside neurons can be modeled by a diffusive evolution equation. And also from this paper, you know that a cable model can model in a nice way a dendritic tree, which is this part of the neuron cell. So this means that the current that flows inside this part of the neurons can be described by this kind of function. And we put this equation on a network structure. So let me spend a few words afterwards. Here I want just to say that V is the membrane potential, and then here we have some constant. In particular, here we have a constant, which is the membrane conductance. So if we want to meet our model here, we don't want a constant. We would like to have a function of time and space. The function of time will be our scalar input control. The function of time will be our operator B. But here, why can be nice to put this to model this part of the neurons on a network structure. In fact, the neurons are the longer cells inside the human body. And in particular, the motoneurons, which are the neurons that are in charge of the movements of the foot and the hands, can be very long. And for instance, for giraffes, they can be long also some meters. So you see that one dimension is much bigger of the other two. And so this means that a one-dimensional model makes sense. And we can model the dendritic tree by this function, this evolution equation on a network. So the boundary condition ensure you that the potential is continuous and the current flowing to the nodes is conserved. So this means that the Neumann-Kirchhoff condition makes sense also in this case. And in fact, for the external vertices, you can put Dirichlet or Neumann. This means that you impose open-end or closed-end condition. So the last thing we are remaining with is the G. But this constant here should be in this work, the authors tells that if you want to model more realistically a synaptic inputs, you must allow the membrane capacity to depend on space and time. And this is very good because here we have exactly the model we have seen so far, posed on a network structure. So now let me go to the application, show you an application to a heat equation on a star graph. So here we consider a star graph with 3 edges. We consider the edges, the external edges as the starting point, the external nodes at the starting point of each edge, and the edge that is shared by the 3 edges as the endpoint of all the 3. So here we consider a bilinear control problem on this particular graph, where our operator B will be the multiplication operator by this function and applies only on the first edge. So what we want to do is to try to control to the first eigensolution the equation on all the graph just by acting on one edge. So this is the problem we want to treat. So you see the control is only in the first edge. We put Neumann boundary condition and the Neumann on the external edges. So the Neumann boundary condition tells you that the first eigenvalues is equal to 0, and you have also an explicit expression of the first eigenfunction. this one will be our reference trajectory. So given a time t, and we want to reach exactly this state if we start in a neighborhood of this function. So if you impose the Neumann boundary condition on the external nodes, you know also that the eigenfunction are cosinus functions. And if you impose the Neumann-Kirchhoff condition in the internal node, you know that the function must be continuous in BI. So this means that the three components evaluated at the internal node must be equal to each other. And you want the zero derivative in the internal node. And this means this condition must be satisfied. So now I want to spend a slide on showing you that if you consider, for instance, the length of the three edges equal to L, things does not work. Things do not work. So why do not work? So here we have that all the three edges have the same length. So from the first Neumann-Kirchhoff condition, you have that these equalities must be satisfied. And this equality is satisfied on one end if you have the coefficient A1j equal to A2j equal to E3A3j. And this means if you put this equality on the second requirements of the Neumann-Kirchhoff condition, meaning that the derivative on the internal node is equal to 0, you find this equality here, which tells you that this sequence is a sequence of eigenvalues. But these equalities can be also realized if the cosinus of square root of lambda JL is equal to 0. We have this equality here. And this tells you that these sequences are a sequence of eigenvalues as well. But then if you consider this equation, you put use this condition inside the condition of zero derivative on the internal node, meaning the second Neumann-Kirchhoff condition, you have that the sum of the three coefficients must be equal to 0. So this means that we are giving a relation between the three coefficients. This implies that these eigenvalues have multiplicity 2. But if you have eigenvalues with multiplicity 2, you don't have any gap condition. So you see that you have to properly choose the length of the edges in order to apply our result. And in fact, if you have that the length of the edges are linearly independent over Q, you have that the Neumann-Kirchhoff condition implies these two equalities. These two equalities, I will need it for proving the assumption on operator B. And here, if you remember, for B, we want that all the Fourier coefficient of B applied to the first eigenfunction are different from 0 and bounded below by a constant times a negative power of the eigenvalue. Okay, so the first one is very simple because you have the explicit expression of the first eigenfunction, and you see that if the first the length of the first edge is different from 0, you have that this is different from 0, so no problem. So the difficulty comes when you want to prove that also the other one are different from 0. So in fact, if you write down the Fourier coefficient of B phi 0, the other ones, you find this expression here. But it is possible to prove, and it's proven in this book, that if the lengths are linearly independent of Q and the ratios are algebraic irrational numbers, Then for any positive unbounded sequence omega k, you can bound by below the cosinus of omega k Lj by this power of omega k. And we use this property 2 times. One times we use in the Neumann-Kirchhoff condition, which gives us the bound from below of the coefficient ak in order to bound here, this coefficient, and directly here. And in fact, using this result, it is possible to prove that also the other Fourier coefficients of B phi 0 are all different from 0 and bounded below by a constant over a positive power lambda k. So this means we have proven all the assumptions we need to ensure the local controllability to the ground state, the first second solution. So let me stress that we were able to control to the desired state our 3-edge star graph because of the proper choice of the length of the edges, having the control just on one edge. We could control the entire graph. So I think that my time is finished. So I just go to the references. Let me skip this part. So here you can find all the references of the works I talked today and some references of some other bilinear control problems. And I can stop here. Thank you for your attention and greetings from Rome. Thank you.
Okay, thank you. Thank you, Professor Cristina. I don't know if there is questions in the audience. So, here. Yes, we have questions. Is the negative result the most when you do the choice of the steady space?
Yeah, they prove that the negative result holds when you take the initial condition in the state space X. And but also if you choose other spaces where A generates a strongly continuous semigroup and also B is linear bounded in these spaces, you are still in the negative result. So here in order to escape from this negative result, you just need to violate one of the assumptions. For instance, you can choose spaces where B is not bounded.
Okay, we have another person. Mohamed. Yes.
Yes, thank you for the call. You heard me very well, please?
Yes, I can hear you.
It's just in page 12, please. In page 12.
Page 12, yes, I can share again. Yeah.
Yes, and display this page.
Yes.
Exactly here.
Yeah.
That's when you take these Hilbert spaces, normally should be the direct orthogonal sum, not the product.
Yeah, product. Let's say, yeah. I mean, each on each edge you take the L2, and then you take yes.
So is the
yeah.
direct
I mean
sum,
the yes,
not
yes,
the product.
Yeah.
The first one, yes. And the other very easy query, what the following page 30, that when you say that that's Neumann boundary imply the Neumann Kirchhoff boundary.
What? Which page? This one?
The Neumann boundary implies the
yeah. So when I look.
the previous one,
previous.
and the page 13. We will remain in the page 13, please.
Okay.
Yes, that Neumann
Boundary condition,
yes,
yeah.
this imply Neumann-Kirchhoff boundary condition, because we take just the sum of the Neumann boundary.
But here, yeah, sorry. Here, when I say Neumann boundary condition, I'm just considering external vertices here.
Ah, yes.
No,
Okay.
Neumann-Kirchhoff are for the internal vertices.
Ah, yes, exactly. Yes.
Mm-hmm.
Thank you very much.
No problem. Thank you for question.
Okay, thank you. I don't know, we have more questions. The audience. So you have a question? Yeah, that's correct. So, well, I guess that we have to say no more than thank you to Professor Cristina.
Thank you.
And
Thank you very much for the invitation.
One of curiosity. You also build a methodology in order to construct the control P, right? Using the moment method, right? That's the contribution.
Yes.
Okay. That was my curiosity, because quite interesting work. So I'm reading your thesis right now. So
Okay. Okay, right.
Thank you, Professor.
No problem. Thank you for the kind invitation. Yeah.
Thank you. I don't know if you have one. So right now, the Prophet Muhammad also writes again, once again.
Yes, thank you very much. Just another small query.
Yeah.
Do you mean about external vertices and internal vertices? What you said? Is
So
that right?
external vertices are the ones that are shared just by one node. And internal vertices is they are shared by more than one node.
Depend of the degree of the.
Yes, in fact. If you have degree 1, you are external. If you are degree more than 1, you are internal.
Ah, yes, okay. Thank you.
No problem.
So, well, once again, thank you, Professor Cristina.
Thank you. Bye-bye.
We continue with the break until 2 p.m. Colombian time. And thank you once again, and bye-bye. See you.